Learn all about databases in this course designed to help you understand the complexities of database architecture and optimization. From understanding the foundational components like transaction management and storage engines, to mastering advanced indexing techniques and exploring the inner workings of SQLite. This course equips you with the knowledge to efficiently manage and optimize data systems. Kirti Perswani developed this course.
A lot of people get confused between the difference of buffer manager and the cache manager. You cannot process things directly on disk. Taking logs is just a part of handling concurrency. These make sure that our DB becomes distributed. This together forms the backend of the database. Software engineers deal with databases on a daily basis. But there are only a few software engineers who actually get to work on these databases, understand truly what is happening inside, and look at the internal architecture. But most of the databases that we use commonly these days are actually open source. So why can't we go through this open source code and understand what is happening inside? You tell me, wouldn't it be so cool and so damn awesome if we could not only understand the internal architecture of databases, but also be able to debug the code? I don't know about you. As a software engineer, I have always wanted to do this, and as a teacher, this has always been in my bucket list. So yes, all of this is finally happening. Introducing to you the free course of Databases in Depth by Educosys, where we are not only going to understand the databases on a higher level and the requirements and all, but we are going to look at the internal architecture, understand why a particular database works in a particular way, and also debug the common queries in all the databases. Now, why am I calling this a free course even though it is going to be available on YouTube itself? Because I'm structuring it like a proper course itself. So let me tell you how it is structured first. This is the first video or the first lecture of the course, and how we are going to get started is we will understand the general components that are there in any database. It will be a great place to start, and you will understand that how data flows, how data is stored, and so on. But as we pick up the databases in particular and understand them in detail, you will understand that some databases obviously focus on some components more. They just call the component something else, or they just combine a few components and again call them something else. But this will be a great place to start, and it will be a guideline for reference as we pick up the databases one by one. So because this is the first video, please note that this is a relatively shorter video. All the videos after this are going to be at least 1 hour long. We will get started with understanding the most important concepts in any database, which are BB plus trees and LSM trees. This will give you an understanding of how data is stored in the most common databases. And once you understand these important concepts, we will get started with the simplest database out there, which is SQLite. Now, every DB that we pick up, we are going to dedicate one video completely to understanding the internal architecture, at least one video. And we are going to pick up one video where we will debug the queries, the common queries. So this is how we will pick up each of the databases one by one. As I said, we will get started with a simple DB, which is SQLite. Then we will pick up more complex databases like MongoDB, Postgres, and so on. So this is how the entire course is structured. And let's get started with the first video. But before that, I would just like to say that if you think this course, this video, or the channel in general deserves to reach more people, please consider sharing it with your friends, maybe on LinkedIn, Insta, anywhere. Please just tag me, share it. You have no idea how much it will mean to me. It will just take 1 minute or max 2 minutes for you, but it will mean just so much to me. It will motivate me to do better and to keep delivering as much as possible. A lot of effort has gone behind this, and a share would mean the world to me. Let's get started with the first video now. In all the databases, we firstly have a client. Now, this is the client that is going to be responsible for performing the CRUD operations, which is create, read, update, delete in the DB, right? Obviously, there is going to be a DB server that is going to be running separately. So this is the entire system that we are going to understand in detail, and we are going to understand all the components inside this. Now, first thing that we want to be able to do is for this client to be able to interact with our DB, right? Now, usually DB runs on a completely different server somewhere on the network. So first thing that we have to do is to be able to communicate between the client and this DB server somehow. So our DB server obviously is supposed to have a network layer which will be responsible for the communication between this client and the rest of the components in the DB. So I'm going to quickly write the network layer over here. Now note that I said that usually there is going to be a separate server for databases because there is one exception. Now most common databases have a server dedicated for DBs, right? But SQLite, which is the most common and the most simplest database for small to medium devices. I was just talking about it that this is one of the simplest databases because you don't even need a separate server for it. It is embeddable. That means you don't need a separate process. It is going to be embedded in the same process as the rest of the system. So it obviously doesn't need a network layer, but for rest of the databases which are commonly used, obviously a networking layer is required. And when we discuss these databases in detail, obviously these nuances are going to be more clear that these components are very important in particular databases. I just told you about it, right? But generally, obviously there's going to be a network layer to be able to communicate between the client and the rest of the components. Coming to the first component, in order to understand what is the first thing that should happen inside the database, obviously we should understand how client is sending the instruction or the command or the query to the DB. It is a simple query, right? That like select all from or like create table or create document or insert into. So it is a command or a query. Now, first thing that DB is supposed to do is to make sense of whatever instruction or command has come in, or is the query even valid. So first thing that DB does is, so this is going to be our first component. And the first thing that DB is supposed to do is to understand that what are the words that have come in and to understand it one by one. So basically select all from or create table or create document. So is create a valid token or a valid word? Similarly, is select a valid word or is insert a valid word? So first component is going to have a tokenizer and it will be responsible for tokenizing the query, basically dividing the query into simple words and tokens so that we can understand that, okay, this might mean this might mean this. Now, once we have divided the entire query into small tokens, we need to understand that these tokens together, do they form a valid statement? Is it a valid instruction or not? Like for example, if I do into insert or if I do table create, it doesn't make sense. Our DB will not be able to make sense of it. So whatever tokens are there, have they come in the right format? Do they together make sense of an instruction or what do they even mean? So after that, we have a parser. Usually databases have the output of a parser as a parse tree, which is going to tell you that what are the instructions that need to be performed. So tokenizer is going to divide your entire query into tokens, and then parser is going to understand that, okay, these tokens together are making sense. This is a valid instruction and this is what our client is asking us to do. So basically these tokens together, are they following a particular rule or not? Are they together a valid instruction? And then what can be done corresponding to this instruction? Now that is what parser is going to do. After that, after we know that, okay, this has been passed, now we know that we need to start executing this particular instruction that we have gotten. But before we do that, our database needs to understand that what would be the best way of executing this query. So for that, most of the databases are going to have an optimizer. Now see, there are many ways of executing a particular query. Our database needs to be fast and it needs to find out the best way to be able to do that. A very simple example is we should be able to understand, do I need to scan all the rows or can I scan just an index in order to be able to go through this query, in order to run this instruction? Or for example, we need to have some joins to run this particular instruction. So how do we execute that? The role of the optimizer is to understand what is the best possible way to be able to run this instruction or to be able to run this query. Is there something that I can do parallelly? So after this, after optimizer, we will have proper instructions or proper operations that the rest of the components need to perform. Now the entire output of this first component can be either in, say, terms of bytecode, or it can be, say, operations or instructions. The main thing is that the output should be such that the rest of the components can make sense of it. So if it is in terms of bytecode or in terms of operations, rest of the components should be able to understand what is it and what are we supposed to do. So these three together, which is tokenizer, parser, optimizer, together form the first component of our database, which you can call as the front end of the database, because this is responsible for making sense of whatever query is coming and converting into something that the rest of the database, or you can consider the backend components together, can understand and execute this query. So this is like the front end of the first division or the first component of the entire database. It consists of usually three things: tokenizer, parser, and optimizer. After the first component, now that we have the optimized plan and we know that what does the instruction actually mean, what does the query even mean, it is time that we can get started with the query execution. Now, this is done by one of the most important components of the entire system, which is called execution engine. You can consider this like the most important part of the entire system because it is responsible for firstly query execution. So query executor. Now query executor is very simple. Whatever instruction it's supposed to get, like, or whatever operations it got, like one by one, just do this. Other than query execution, it also does cache management. So there is a cache manager inside. Why cache management is needed? Obviously, it doesn't make sense to keep querying again and again. If we can just cache it, then we should be caching it. You know about caching, right? To make it faster. We'll cover it in a lot more detail in the coming videos, of course. But you should understand the basic concept that we need to cache some data instead of querying again and again. So a cache manager is needed. Other than this, there are also some utility services inside the execution engine. Like for example, for authentication or security or backup or metrics. For these things, there are some utility services inside the execution engine. Now you must be thinking that, Kirti, didn't we just do the query execution? Shouldn't this bring us to the end of the entire system? No, not really. See, in databases, transaction itself is a very complicated term. It's not as simple transaction as it sounds. Let's take a very simple example. For example, we have to transfer money from A person to B person. That means that we have to first reduce the money amount from the A person and also increment or give the money to the B person, right? So one transaction itself involves two steps. Similarly, usual transactions in our real databases and in real scenarios are going to be very complex and are going to consist of multiple steps. Now, all databases do not support ACID properties, but a lot of databases do. Now, all databases, the other databases also, are supposed to have ACID properties to some level, right? Atomicity, consistency, isolation, durability. Especially atomicity, doesn't it make sense that all databases should have some level of guarantee that either the transaction is going to get completed or it is not going to get completed. Similarly, consistency, isolation, durability, all of this. So it makes sense that there is one component that is going to be dedicated to make sure that the transaction management happens properly. So that is why we have a transaction manager, which is going to make sure that these things happen properly, the ACID properties are followed. Now, as we do transaction management, a very important thing that we have to do in order to make sure that when there are multiple transactions, there are no data inconsistencies or conflicts or data anomalies, we have to take some logs, right? That is how things work in real systems. Now, different databases are going to manage logs in a different way. Some are going to take shared logs, some are going to take exclusive logs. Some databases are going to take logs, say, over a particular row or over a particular document, while some other database might take a log over entire database itself. That is also possible. Now, the way of handling is different, but definitely it makes sense that every single database is supposed to take care of multiple transactions. So obviously, log management is again very important. So we can again take care of transaction management, log management. Now, as we're talking about transaction management and log management, one very important thing to talk about is that suppose in between the transaction, a crash happens and our DB crashed. So now what is going to happen? How are we going to recover from it? Did the transaction finish? Did it not finish? Do we have no idea how to go on from there? Right? So how do we recover from the crash? So a very important component is going to be recovery manager. And these together, the transaction manager, the log manager, the recovery manager, form our next component. We discussed that in order to handle multiple transactions at the same time, we can have a log manager which is going to take care of logs. In other words, we want to take care of multiple transactions concurrently, or we want to take care of concurrency, which just means that take care of multiple transactions at the same time. When we want to take care of it at the same time, we just say that we want to take care of concurrency. Now, the thing is that taking logs is just a part of handling concurrency. If we want to talk about concurrency at a broader level, how to take care of concurrency, most of the databases take care of concurrency by using other techniques also. For example, a very common technique that is used by a lot of databases is called MVCC. It is multi-version concurrency control. There will be a dedicated video in this course where we will be talking about MVCC because it is actually used by a lot of databases. So in short, there are other techniques as well that databases employ to make sure that we can handle concurrent transactions at a broader level, and log management is just a part of it. See, when we are designing such a huge system like a DB, it makes sure that we have separation of concerns so that our system is flexible, it is maintainable, it is extensible and all of that, the usual guidelines for system design, right? So that is why usually there is a separate concurrency manager altogether. Now I could have added it in the last component as well, but I'm just telling you that concurrency manager and lock manager usually work together. But there is a clear separation of concerns that concurrency manager will take care at a broader level that the transactions can happen concurrently. Whatever is the level expected from that particular database, it will take care of that. Taking care of the logs is just a part of that, and log management will take care of it. Next question that must be coming to your mind is that, Kirti, we talked about execution engine, transaction management and this and that, but how does data actually get stored on disk? Because in the end, data is going to get stored on disk. So how does that happen? How do we retrieve the data? How does the processing happen? Who is taking care of that? And yes, that is where our next component comes into picture. And as you must have guessed, it is an extremely important component. It is called the storage engine. As the name suggests, it is going to take care of everything related to storage. Now, let me give you some context about it. We are going to be discussing about storage engine in a lot more detail in the coming videos, but I'll give you some quick context for basic understanding. So firstly, we need to store data on disk, right? So obviously there's going to be a disk storage manager. And this is where the knowledge of B plus trees and LSM trees is going to come into picture. Why do we need them? Why are they so commonly used in databases? We are going to be discussing it in a lot more detail, but just understand this for now. See, disk is basically just like a circular proper disk. It is actually cheaper than, say, our RAM. So that is why we store data on this, and also we get persistence, right? If we store something on RAM and it crashes, it is gone. So in order to have persistence, in order to make sure that we can store lots of data in a cheap way, disk is used. Now, how does disk look like? How is data accessed? See, disk is divided into, say, circular tracks and some pie shaped. So it looks something like this. So this is how disk is going to look like, and there are, like, say, circular tracks like this. So every small component is called a page. Now whenever you want to access something on disk, the entire page from the disk needs to come to memory. Then you can do whatever you want with it, and if you want to even update it, you need to process the entire page and put it back. This is how it works on a higher level. Trust me, we're going to discuss in a lot more detail, but the main thing that you should understand is that you cannot process things directly on disk. You need to take it, like, bring it to the buffer, manage it, process it, whatever you want to do, and then put it back. So this is where we need another component, which is called buffer manager. Now, a lot of people get confused between the difference of buffer manager and the cache manager. So let me just make things clearer. See, caching is something that we again do for, to make queries faster only. But it is something that we can do at all levels. So you must have heard that caching we do in the front-end systems, in the back-end. So in DB, it is happening at the execution engine, as we have already seen, right? But what happens is that there can be different mechanisms for caching, like there can be LRU, LFU, and so on and so forth. This is to make the executions faster. It is a very broad concept to take care of and to make queries faster. Buffer manager, on the other hand, is to make sure that we can deal with the data that is there on disk. So how do we do that? So we have to first take out that data in terms of pages and fixed size pages. So on disk, everything that you store is in fixed size pages, like say 4 KB. So you bring the entire 4 KB to buffer, deal with it, and then put it back. So that is why you need a buffer manager. So there is a disk storage manager, there is a buffer manager. Now the thing is that dealing with disk takes a lot of time. It is a very expensive operation, and especially that we have millions of data, billions of data. A very important thing that needs to be done is to make sure that this happens very fast, right? And this is where, a lot of discussions and a lot of databases happen, that which storage engine a particular database is using. You must have heard, like for MongoDB, the storage engine is called WiredTiger. Their storage engines have evolved over time because it's a very core concept, a very important concept of a database. How fast or slow your database is going to be is really dependent on storage engine. How fast can it retrieve the information? How fast can it update the information on the disk? So that is where the concept of making this retrieval as fast as possible comes into picture. And in order to do that, you make sure that minimum number of reads are required from the disk, and you are able to get that particular data that you are looking for in a very fast way. And this is where indexing comes into picture. We will again discuss it in a lot more detail in the next video itself. So make sure you subscribe and make sure that you don't miss that video, because it's going to be an amazing video. Your entire concept of why do we need BTrees, why so many databases use BTrees, why indexing, and how much does it actually improve in terms of efficiency. We will cover all of that. I will actually show you that, see, by this many times we are actually improving the efficiency. So it's going to be amazing. But over here, the main point is that we need an index manager as well. In short, storage engine is the core of our database, and it takes care of disk storage management, buffer management, and index management. It also takes care of a lot of other things also, but these three are its main functionalities. Coming to our lowest component in databases, see, when dealing with disk, anyway we have to deal with what? We have to deal with disk files. Now OS plays a very important role over here. See, we might be using Mac or Windows or Linux and so on. See, every OS is going to have its own system call. Like for example, if you're doing file.open, the system call is going to be different, say for Mac, for Windows, for Linux. And our DB is supposed to support all, and it is supposed to have an interface. So there can be the lowest layer, we can call it as OS interaction layer. Or you can see it as a file system interface. So this is nothing but we are making the system call according to whatever OS we are using. As you can see, I have left some space over here. Does this mean that I missed one component in between? Not really. See, whatever components we have covered so far, these together are enough to understand the general components that are there in one DB server. But the truth is, in reality, it is rarely just one DB server, right? Nowadays, we want our DBs to be what? Highly available, to be scalable. We want to be able to store millions and billions of data. So how do we do that? We obviously cannot store everything on one DB server. There have to be multiple DB servers. So in order to handle DB server distribution, to take care of the distributed components, there is another component which we can talk about. See, the thing is that as our DB is going to grow, as the amount of data is going to grow, say initially there were lakhs of data, then it grew to millions of data. As the amount of data keeps growing, it will not be possible to store it within one DB server, right? Just one disk. So it will make sense that we have multiple DB servers. So we will divide our entire data into small parts, not small parts, into parts, or we can say into shards, correct? So we need what? We need shard management. So we will have a shard manager which will take care of that, okay, this data is going to go into which shard. So based on some factors, we can have sharding, and so we need a shard manager. Now the thing is that this will make sure that our DB is scalable, but now we also need to manage these multiple nodes, right? So there are going to be a lot of servers together in a particular cluster. So all these servers together can form one big cluster, and we will need a separate cluster manager for that. And now we talked about scalability, but availability is again extremely important. We always have a trade-off, right? Consistency versus availability, CAP theorem, very, very important. So when we talk about availability, the first thing that comes into mind is replication. So obviously in our DB also we have replication, which is actually extremely important. We talk about this a lot, right? So we need a replication manager for that. So all these three components that I have written right now, these make sure that our DB becomes distributed and we can handle availability and high scalability. Congratulations, you just understood the general components and the general internal architecture of DB. As I said earlier also, it is going to vary slightly in all the databases, of course. Each database is designed in its own way, but this will be a great starting point for you. You will be able to understand that, okay, this is the component that we are talking about. This is how the data is flowing. This is what needs to be happen in any DB, right? So let's do a quick revision for you to be able to understand it together just once, right? So let's do that. So our client firstly needs to talk to our DB system, right? So there needs to be communication between client and our DB server. So our network layer is going to take care of the communication between client and the rest of the components. Then there is front end, which is responsible for just converting whatever query is coming to us to something that the rest of the components, or you can say this together forms the backend of the database. So front end is making sure that we convert the query into something that our backend can process, understand everything, right? So the query that is coming is in terms of English or any commands, any instruction format that we are given. Like for example, in terms of SQL databases, it is going to be a SQL query, right? Similarly, it is going to vary per database. So first thing that we need to do is first tokenize the query, understand what it means, then together see, is it following a particular grammar rule, or does it make sense to form some instruction? So we are going to parse it, and then we are going to optimize it and find the most optimal way of dealing with that particular query. Then our front end is going to pass whatever instructions we have to our execution engine. Execution engine is going to make sure that our query executed properly, and it is also going to take care of the cache management and utility services like auth, backup, metrics, and so on. Then we need to take care of our transaction management. So all of these components together are taking care of transaction management, within which we are going to make sure that if needed, we follow asset properties, we take care of atomicity, consistency, isolation, and durability. So there is log management, which is going to help us take logs at different levels. There's recovery management, which is going to help us take care with the crashes within the DB, transaction management, and concurrency management. Now, as we discussed, log management and concurrency management are going to work together to help us take care of multiple transactions at the same time. Concurrency manager is more broader, and it sort of uses log manager. And one very common technique that we are going to be discussing in the course is going to be MVCC, which is multi-version concurrency control. Other than this, we talked about that this is going to help us make sure that our DB is highly available and scalable by helping us take care of distribution of DB servers. So we are going to be sharding our data based on some particular parameter. So this is going to take care of sharding, this is going to take care of cluster management, and this is going to make sure that we have backup of the data, we replicate the data, so replication management. Then comes another very, very core component. So execution engine is very important. Then storage engine is again extremely important. It takes care of how do we really store the data on disk, how do we process it, so how do we take out the data from the disk to the buffer, how do we process it, and how do we make this process as fast as possible, how do we make the retrieval as fast as possible by doing indexing. Then we know that we have to deal with disk files. So there is one OS layer which helps us deal with different OS like Mac, Windows, Linux, and so on. So this is how our general DBs are going to look like. And I hope you are excited to start diving into DBs individually. Again, we're going to be starting with SQLite. We have optimized from 100 seconds to 250 milliseconds to 3 milliseconds. We have seen number of comparisons that are required for 1 million records. So you can see this is the most efficient solution. There is a huge improvement as the number of entries grow, and that is what BTree does. Why do so many databases use BTrees and B+trees? Are these really more efficient than say BSTs or arrays? And if more efficient, how much more efficient? Is it okay to use BSTs or arrays in case of databases, or are BTrees really necessary? How do BTrees even work internally? Can we do a dry run to understand it in a simple way? What is the difference between BTrees and B+trees? Are they same? And yes, we are going to cover all of this in this video. And welcome to another video in the free course of Databases in Depth by Educosys, where we not only discuss databases in theory, but we debug their code. And yes, in the next video, we are going to be starting with one of the most common databases, which is also one of the most simplest databases in the world, which is SQLite. But before getting started, it is very important that you get your basics right. And that is why this is an extremely important video. Let's get started. Whenever we think about storage, we think of two solutions. One is RAM and the other is hard disk. Now you might think that this is very basics, but it is very important to get our basics right and to build up the use case. So just stay with me. So what about RAM? RAM, as we know, is temporary. That means that if it crashes, it's gone. We lose our data, right? It is volatile is another term, which means that it is temporary. Also, it is expensive. And because of that, we have limited space in RAM. What does that mean? That if our database is obviously growing, if we have terabytes of data, we cannot store it in RAM. RAM is very, very limited. It is expensive. So that is where hard disk comes into picture. Why? Because hard disk gives us persistence. We are able to store the data permanently, right? And there is no limitation as such. We can keep adding hard disk and we can store TBs of data. It is also very cheap. Then hard disk is the way to go. It is awesome, right? Not really, because it takes more time for every IO operation. For a simple comparison, let me just tell you that if you are doing one simple IO operation in RAM, it might take time in some nanoseconds. Obviously, the exact time is going to vary, but let's say 1 to 10 or max 100 nanoseconds. Versus in a hard disk, the same one IO operation is going to be in milliseconds. Yes, just literally one IO operation can take up to say 1, 10, 100 milliseconds. So we know that each IO operation is expensive. It takes some time in hard disk. But it is very important for us to understand that why is it so? How does a hard disk look like? How does it operate? So hard disk is nothing but a circular disk platter, and how it is divided is that inside it there are some concentric circles. So these circles that you can see, these are called tracks. So each of these concentric circles, this is called a track. And then you divide this disk also into some pie-shaped pieces. So you see these pie-shaped pieces, each of them is called a sector. So like this is one sector, okay. Now what will the intersection of a track and sector give you? So if you see, if we consider this track and if we consider this sector, what will it give us? This particular block, correct? Similarly, if we have to consider just this one block, this is what? This is intersection of this track and this sector. Similarly, if I have to consider this block, it is intersection of this sector and this track, correct? So intersection of a track and a sector is giving us what? It is giving us a file block. So now typically the file block on a disk is of the size of 4 KB. Obviously it varies with the disk. It can also be say 16 KB or like 512 bytes, but typically it is 4 KB. So what happens is that whenever we have to do an IO operation like write or read operation, what happens is that we can always read and write in terms of file blocks. What do I mean? For example, if we have to consider some data which is over here, okay, so this is one file block and we are considering data over here. Now there is some data on the left, there is some data on the right, but it is not like I can take out just this particular data. It is not like that. In order to process it, in order to process that data, I have to take this entire disk block from the hard disk to RAM. So in order to process any data, what we have to do is we have to take the entire file block from the hard disk to the RAM. So whenever we have to do any processing, like suppose we have to process some data over here, we have to take out this entire file block, get it to RAM, process it, and then put it back. You cannot directly process it over here. So the CPU can access the data that is there in RAM and it cannot directly process the data that is stored on hard disk, not directly. So whenever you have to process any data, you have to take the entire block from hard disk to the RAM, process it, if update is required, put it back to the hard disk. So this is how it works. But let's understand what is the impact that it has on us. Let's take the example, suppose we have 1 million records. Suppose we are dealing with 1 million records. Now, if we are dealing with say SQL data, each record is going to be a row. Suppose we are dealing with NoSQL DB, like for example, MongoDB, we are going to call each record as a document. So now each record can be a row, it can be a document. In our case, let's say that each record is an entry. Okay, so each entry, for example, is taking 400 bytes. So this is per entry or per record. Now it can be a row or doc or anything. Now what might happen is that there might be like huge doc and inside that maybe some string is taking 50 bytes. There are like 4 integers, 4 bytes or 8 bytes like that, right? So maybe total is 400 bytes. So 1 million records and 400 bytes is per entry. So now first thing that we have to understand is that one block can store up to 4 KB of data, correct? One block can store up to 4 KB of data. So this is what we said, right? So that means how many entries or how many records can it store? That means 4000 bytes divided by 400 bytes. That means one block can store 10 records or 10 entries, correct? Every single block, so it might be something like this, 1 to 10 over here, 11 to 20 over here, 21 to 30 over here, 31 to 40 over here, like this. So every single block would store 10 records or entries, correct? So I'm assuming that every file block can store up to 4 KB and every entry is taking 400 bytes. So this is just an example to understand. Okay, now in order to read 1 million records, let's see how much time would it take. So if we have 1 million records, that is 10 power 6 records, right? How many blocks would we have to read? Number of blocks to be read would be 10 power 6 divided by 10, because every block is storing 10 records. So how many blocks are required? 10 power 6 by 10, which is 10 power 5. So we have to read 10 power 5 blocks to go through 1 million records. In order to go through 1 million records, we are reading 10 power 5 blocks. And we said that in a hard disk, one IO operation takes, say, 1 millisecond. It can also take 10 milliseconds, but let's say it is taking 1 millisecond. Okay, if it is taking 1 millisecond, that means that this is going to take 10 power 5 milliseconds. That means it is going to take 100 seconds to read 1 million records, which is huge. So in order to just read 1 million records from the hard disk, we would take 100 seconds. We should obviously try to make this better. Now that is the problem that we are trying to solve. So what did I do? I just took some example. 1 million records is a very common thing in databases, right? 4 KB is the standard thing. Your document can be this big. So even if not 400 bytes, maybe even 40 bytes, even if it is taking 10 seconds, it's a lot of time. So we want to minimize the time taken to go through the records. How can we do that is the problem that we are going to try to solve. Before we move ahead, I would just like to take a minute over here to tell you that if you are preparing for interviews or if you are looking to become a better software engineer, I would love to be part of your learning journey and make it easier, faster, better and more fun. I teach live, plus you also get access to the recordings so you can learn at your own pace, and you get a consistent teaching style because I teach all HLD, LLD, DSA, project-based courses where we cover industry-level projects like YouTube, WhatsApp, Zerodha. We cover MERN stack as well as DevOps, and we also have C++. Plus, if you sign up for any of our courses, you get lifetime access to all the batches, the past, present, future, everything. You also get access to our mock interview platform. You can come practice anytime. We are going to guide you. We obviously have doubt support as well. We are putting our heart and soul into teaching. So if interested, at least check out the site. All the detailed curriculums, the testimonials, the answers to all the general FAQ, everything is present over here. Just check it out. Educosys.com is the site. Plus, if you still have any questions, feel free to reach out to us at support@educosys.com. We will also guide you about what is better for you. At least check out the testimonials for now.
The best thing that I like about Educosys is their courses are live.
Kirti herself, the way she teaches, the way the courses are structured are actually the best part.
Their live classes and the very helpful Discord community.
I feel very confident as compared to what I was before these courses as a software engineer.
My experience at Educosys have been really great.
I feel more confident as a software engineer after enrolling in Educosys.
But for now, let's get back to the video. Let's consider a very simple solution. So I have drawn a disk over here. Let's say that, okay, here there are records. So 1 to 10 are over here. Again, 11 to 20 are over here. 21 to 30, just how we saw. Okay, so records are over here. Now what we are going to do is we are going to have yet another table. And what it is going to store is, it is going to store, suppose record 1, it is going to say that from record 1 till the next entry. So suppose my next entry is 11. So from 1 to 10, all the entries are over here. Similarly, from 11 to say 20, all the entries are over here. So we have a pointer to that particular block. So we know that if I just go through this table, I will know exactly where the entry is. So instead of going through all the how many blocks, so there were 10 power 5 blocks, right? So instead of going through all the 10 power 5 blocks, now let's see that how many blocks will we have to go through. Okay, now what is going to happen is, obviously this table is again going to be on disk, right? So this is also going to take some space. It is also going to take some extra file blocks, right? So we'll have to see whether it is actually more efficient or not. So let's do the calculation and let's see. So approaching the problem in a similar way. So first thing that we have to see is that in one particular block, how many entries can we store? So one block can store 4000 bytes, right? Obviously, this is all rough estimation, by the way. So when I say 10 records, it is roughly because it is 4 KB. So I'm considering it 4000 bytes. So obviously, this is all rough estimation. Okay, just I hope you understand that much at least. So let's see that how many entries can we store. Let's say that each entry in this particular table is taking, say, 10 bytes. Good enough estimation. Maybe it would be 12 or something, but 4 and 8. So maybe we can take it as 10 bytes. Okay. So if each block can store up to 4000 bytes and each entry in this table take 10 bytes. So that means that each block can store how many entries of the table? That means 400 entries. So every block can store up to 400 entries of this table. Versus if we consider the data entry, how many entry was that? So per block we were storing only 10 entries because that was a huge data entry, right? It was of 400 bytes. Over here it is of only 10 bytes. So each block in this case is going to store 400 entries of what? Of this table. Now again, how many such entries are going to be there? So that depends on how many blocks are there, correct? Because how many do we need? How many ever blocks were there in the data? And how many blocks were there? 10 power 5 blocks, correct? So we need the table for what? We need the table for each block. So 10 power 5 entries are there in this particular table. So 10 power 5 entries are there in this table. So the next question is, in order to read this entire table, how much time are we going to take? So we have to read through how many entries? 10 power 5 entries in this table. I hope you understood why we need 10 power 5 entries. See, what are these pointing to? These are pointing to these data blocks, right? These file blocks that are storing data. And how many blocks are storing data? It is 10 power 5 blocks. So that is why the number of entries in this table is 10 power 5. Now we know that 400 entries of this particular table. So if this entire thing is, say, 10 power 5, we can divide into parts, say 400, then 800, then 1200, so on, right? So each of that can be stored in one block. So how many blocks do we have to go through for this entire table? So the number of blocks is going to be what? 10 power 5 divided by 400. So if I just write it in very simple terms, I'm doing the calculation also over here. So this is going to be 250. So we would have to go through 250 blocks of the disk in order to go through this one entire table. And now when we go through this one entire table, that is when we are done going through the 250 blocks, we would have found the data that we are looking for in one of the blocks. Suppose it pointed over here. Now this one data also we would have to read. So this would take one extra 1 millisecond also. So don't forget that. So we are going through the table by going through the 250 blocks. And after that, we are going to see that where is the data. Then we are going to access that one particular block. So how much time will this take? 250 blocks, right? And every block takes 1 millisecond roughly. So that means 250 milliseconds plus 1 milliseconds. But roughly we can say that we are going to take 250 milliseconds to find something in 1 million records. So we have optimized how? We have optimized from 100 seconds to 250 milliseconds, which is huge. How did we do that? By adding this one table. This table is called index table, and you just understood what is indexing and how does it work, how is it more efficient. I am sure that calculations would have definitely overwhelmed some of you. I am going to quickly summarize it and it will be completely clear. Just be patient with me, and if you still have doubts, just go back. Try doing the calculations yourself. It would be just so amazing if you can understand how we were able to optimize from 100 seconds to 250 milliseconds, because this is just amazing stuff. This is real stuff that we are understanding. Okay, so let's quickly summarize. First, we saw that we have 1 million records. We said that every record is roughly taking 400 bytes, and because every file block can store 4 KBs, we saw that one block is going to store 10 records. That means that the number of blocks that we are going to require to store 1 million records are going to be 10 power 5 blocks, which is going to require us 100 seconds. So how many blocks are used to store all the 1 million records? That is 10 power 5 blocks. So on the disk, 10 power 5 blocks are used to store all the data. Then we said let's optimize the time, and that is why we drew this index table. Now in this index table, what did we see? We saw that because each entry is much smaller, it's not like 400 bytes, right? Because each entry is much smaller, say 10 bytes, here we can store 400 entries in one block. Because we can store 400 entries in one block, that means these entire entries are going to go in one block. These entries are going to go in another block. These entries are going to go in another block. These entries are going to go in another block, and so on. So we saw that 250 blocks are needed for the index entries. Firstly, if you still have the doubt, how many entries are going to be there in this table? 10 power 5 entries. Why? See, 10 power 5 blocks are used to store the data. What are we pointing to? The blocks that have data, right? How many blocks have data? 10 power 5. So that is why 10 power 5 entries. So first of all, this should be clear. 10 power 5 entries. Why? Because we are pointing to data. How many blocks are pointing to data? 10 power 5 blocks. I'm again and again repeating so that you don't have any doubts. I'm sorry if you're getting annoyed by my repetition, just making sure that there are no doubts. Okay. Now, if you also want to do the cross calculation, you can see that, 400 entries, and then I'm saying 250 blocks, right? So this will be 10 power 5, right? So this is 100 and then 3 more zeros, so 10 power 5. So that is why, see, this is one block on the hard disk, this is one file block on the hard disk, this is one file block on the hard disk, and so on. So that is how we optimized from 100 seconds to 250 milliseconds. But now the question is, can we optimize this even further? Let's see if it is possible. So what I am going to do now is, I am going to create yet another table. And I am again going to store index only in this. But now this is going to be pointing to one block that is storing our index entries and not the data entries. So there are 2 power 5 blocks for data, 250 blocks for index entries, right? So how many entries are going to be in this table? 250 entries, correct? So this is pointing to this block, this block, this block, so on. How many blocks are there? 250 blocks. So there are going to be 250 entries inside this, right? Let's see how much space is this table going to require. So again, the space for each record is same only as over here, right? What did we see? 10 bytes. So if we come back over here, and so 10 bytes for every entry, and then there are 250 entries, right? So how much space do we need to store this entire table? 250 entries into 10 bytes, which is just 2500 bytes, which is actually less than 4 KB. And this entire table is not even going to require one entire file block size, correct? So now if we have to find something, we can just take out whatever one file block is there for this one table. We will go through this. Then we will see that, okay, if we are looking for something over here, we will see that where is this particular block. Then we will get that one block over here. And then we will go through this one block and we will see where exactly is the data. So how many IO operations are we doing with the disk? 1, 2, and 3. So 3 IO operations, each taking 1 millisecond. So now we have optimized to what? 3 milliseconds. So we went from 100 seconds to 250 milliseconds and now to 3 milliseconds by just adding one more table. And this, my friend, is called multi-level indexing. And guys, we didn't just understand the concept of multi-level indexing, but we actually also drew our very first B tree. And let me show you how. This is going to be very interesting. So what I'm going to do is, I'm going to copy this diagram and I am just copying it. I'm going to a new page and just going to paste it, and I am going to rotate it. And this is exactly B tree. And let me show you how. So if you see over here, there are many keys and there are child pointers. And child pointers are again pointing to some other nodes. And within this also, again, there are some pointers, right? On a higher level, this is how B tree looks like, but we are going to go into a lot of detailing. We are also going to dry run. But before that, I think it is very important that we answer a very, very important question. That is B tree the only solution? What if we used other data structures that are commonly used? So what we are going to do is we're going to draw a table and do proper comparison. We are going to take the example of 1 million records and we are going to compare the time complexities. So we are going to be comparing using 3 most common DB operations that we perform. That is, we usually perform search, we perform insert, and then we perform deletion, correct? So we are going to consider these 3 operations, and then we are going to consider all the data structures one by one. The most common solution that is going to come to your head, like if you did not know about BTree, would be balanced BST. Why? Because it is the most common solution, right? It offers us logarithmic time for searching, insertion, and deletion. So if we consider 1 million records, what would be the answer? So if we have 1 million records, log base to 10 power 6, this roughly comes out to be 20. So that means we would have to do 20 IO operations with the hard disk for search, insert, and delete. How it would look like is, like suppose we have like a root and we know that where it is on hard disk, we get this. And then we will compare and then we will see that, okay, is it on the left or on the right? And then we are going to say that, oh, it is on the left. Then we are going to access another one again from the DB, right? So like this, we will have to do how many IO operations, because for every single node, we will have to do one IO operation, right? So it is going to be 20 IO operations for 1 million records. Obviously, unbalanced BST would be worse than this, but let's do a quick comparison for that also, so that clarity is there and there is no confusion left. See, what is the difference between balanced BST and unbalanced BST? Like if we are storing 1, 2, 3, right? So the correct way of storing is like this, 1, 2, 3. This is balanced. In unbalanced, we could also store like this, because this is also a BST, right? This is also a BST, but this is not balanced. So suppose if there are 1 million records, that means that we could actually store 1 million records linearly itself, right? In an unbalanced BST, it is also a possibility. So how many, worst case, how many operations would we have to do? 10 power 6. Which is obviously not efficient. We would have to do 1 million disk IO operations just for searching through 1 million records, which just doesn't make sense. And if we consider this worst case of unbalanced BST, basically the linear structure, then again insertion deletion will also be 10 power 6. So obviously this is not the efficient approach. Now let's compare for a sorted array, because now you might be thinking that, Kirti, what if we just store all the data in a sorted way one by one? So basically in a disk, how we would store is 1, 2, 3, like for the ID, we would just store like this. Let's see what would be the complexities in this case. See, search would be very simple. It would be binary search like balanced BST itself, which would have logarithmic time. So 20 IO operations, just like over here, right? Because it is sorted, so searching becomes very efficient. But now insertion and deletion is a bit tricky. Now let me tell you how. If you have blocks like this, which are sorted, if you want to insert a new block over here, what you would have to do is you would have to make space for it, and you would have to shift these blocks. You would have to shift these elements, right? So in the worst case, you might end up shifting all the elements. So in the worst case, you would have to actually do 10 power 6, which is 1 million operations for both insertion and deletion. Similarly for deletion also, right? If I am deleting this, I would have to shift all the other elements or all the other blocks. If you want to store it in sorted order, and if you want to insert in between, you would have to shift the rest of them. Correct? That is how it works. So this is an interesting point to keep in mind when we talk about databases, that operations are not similar to data structure operations that we usually consider in RAM. Here we are talking about hard disk, and we have to think that every IO operation is expensive. And finally, it's time that we talk about our star, which is the BTree structure. Now, in BTree, what happens is that we have a minimum and maximum number of keys that it can have, that every node can have. Like over here, we saw that there are multiple keys and then there are child pointers, right? So BTree is nothing but a special type of M-way tree. So we will understand it in more detail. What is M-way tree? How binary trees have like two children, right? M-way tree can have M children. So whenever we have like a lot of data, it makes sense that maybe we can have multiple children, and I will show it to you how. Now this is a special kind of M-way tree. Now in BTree, if we say that the order is M, that means that the maximum children that it can have is M. So there are ways to prove this, but to make things easier for now, I am just telling you that search, insertion and deletion in a BTree, what is the complexity? Log of whatever n, so in our case 10 power 6 base m. So m is what? The maximum children that every node can have. So suppose we consider a BTree with maximum children 100. So then in that case it would become log of 10 power 6 base 100, which would become equal to 3. So we would essentially need just 3 IO operations for all search, insertion as well as deletion. And we actually saw this in our example. We did the calculations and saw that with 1 million records, it is possible that we need only 3 IO operations for search. So this is actually possible, and now the comparison is complete. If you want to draw the proper table, let me just draw it properly and show you. I created this nice table for your reference. You can either take a screenshot or you can share it on LinkedIn or anywhere that you studied something nice if you're interested. Otherwise, let's do a quick recap, a quick summary of whatever we understood so far. See, we have seen number of comparisons that are required for 1 million records. So in a balanced BST, everything is logarithmic. So log base 2 of 10 power 6 is roughly equal to 20. It is 19 point something. So search, insert and delete will require 20 IO comparisons on the hard disk. Versus in unbalanced BST, because it is unbalanced, it can be completely skewed. So the height of the BST can actually be 10 power 6. So the number of operations will be 10 power 6 itself, which is 1 million. In a sorted array, for search you can do binary search, but for insertion and deletion you will need shifting of the elements. That is why it will take 1 million IO operations. Versus for a B tree of order 100, what does order 100 mean? It means that any node can have maximum 100 children. Then we can perform search, insert and delete in just 3 IO operations. So you can see this is the most efficient solution. After this, there is definitely balanced BST. But if you think, there is a huge improvement, and that is why BTree is used by so many databases now. It's finally the time to understand the structure of BTree in detail. So what happens is that unlike BST, where every node can have only one key, here a node can have multiple keys. So what happens in BST, suppose the root node has the key 20. So we see that if we are searching for something less than 20, we'll go here, otherwise more than 20 will go over here. Now in databases, what happens is that even when you're searching for one key, you will anyway have to access the entire file block from the disk. Correct? That is the basic that we need to understand. So instead of doing that, why don't we store multiple keys in a particular node only? Now, how does this help? Actually, we need more comparisons now. See, let me explain you it in detail. So suppose the keys that we store in this particular root is 100, 200, 300, 400. So what is going to happen is that what this is going to point, suppose again here, all the key values are going to be lesser than 100. Over here, it is going to be between 100 and 200. Over here, it is going to be between 200 and 300. Over here, it is going to be between 300 and 400. Over here, it is going to be more than 400. So if I have to see something like suppose 10, 20, 30, 40, over here, it will be 110, 150, 180, 190, like this. So here also we have to do comparisons only. In fact, for every node, we have to do more number of comparisons, because earlier in BST, what happened? We just saw 20, oh, less than 20 or more than 20. Over here, there is one node. We have to see, oh, is it between 100, 200? Is it between 200, 300? Is it between 300, 400? Even though the number of comparisons are increasing, the major thing, our major problem is being solved. What was our major problem? The cost of getting this data from disk to RAM. Now, this is much more expensive than the number of comparisons that you're doing in RAM. And that is why this is more efficient, because even though you're storing more number of keys, all of this will fit within one block. And best would be that, you try to maximize the number of keys that you can fit in a block. Why? Because anyway, if we have to access just this also, you will have to access the entire file block anyway. So it is better to access the maximum number of keys in once, and then we can compare accordingly. Right? So there is a trade-off over here. If we had only one key in the node, then also we would have to anyway get the entire file block from the disk, but the number of comparison would be 1. Over here, the number of comparisons is more than 1. There are multiple number of comparisons, but the cost of getting the data from the disk to RAM is saved. And that is why BTrees is so much more efficient for databases. So I hope now core concept is clear. Let's understand the major characteristics of a BTree now. When we say that a BTree is of order m, so I said this before also, this means that the maximum number of children that any of the nodes in the BTree can have, the max number of children is equal to m. That means that the maximum number of keys that any of the nodes can have is equal to m minus 1. Why so? Why did this happen? We did not understand. So let's see this example. Here we saw that max children are what? Say 5, right? So if the children is 5, see the keys are only 4, which is 1 less. Why? Because see here it is pointing to all the values that are less than 100, more than 100 and in the between values, right? So even though the keys are 4, the number of children are 4 plus 1, which is 5. So if we say maximum children can be m, then the maximum number of keys can be m minus 1. Similarly, B-tree ka property says that the minimum number of keys that any node other than the root node should have m by 2 ka seal. That means that you round off to the next bigger integer. So you take by 2 and then you round off to the next bigger integer. That is what taking seal means. Now root is an exception. It can have minimum 1 key also. So at least 1 key is what the properties say. So root can have minimum 1 key, but all the other nodes should have minimum m by 2 keys. So these are the main properties. If you just see the max number of keys, the min number of keys, you should be able to understand that this B tree will have maximum how many keys, minimum how many keys. Let's take quick examples. So say if m value is equal to 4, that means the maximum number of keys possible for every node is 3. Any of the nodes, okay, maximum number of keys is 3. Minimum number of keys will be what? 4 by 2, which is 2. If m is equal to 5, the maximum number of nodes that is possible is 5 minus 1, which is 4. The minimum number of nodes. So 5 by 2 is what? 2.5. So you round it off to the bigger integer, so which is 3. So this is how you can see that the B tree of order m can have minimum how many and maximum how many nodes. Now because of these two characteristics, what happens is that as we go down one level in B tree, with every level, the number of keys that any level can store becomes byproduct of m. So it becomes m times. So let me explain what I mean. So if from root I have m keys, so my next level will have m into m keys, because m can go over here, m can go over here, like this m times, right? So m into m. Similarly, in the next level, it will again become m times. So m into m into m. So as we go one level down, our number of keys that can be stored at that level will become m times. So if I have to find the height of the tree, because my height of the tree is going to be balanced, a very, very important characteristic of B tree is that all the leaves are at the same level. All the leaves are at same level. So if I have to find the height of the tree, how can we do that? So if I have to find height, if the total number of keys that I have to accommodate is n, then by every level, if I go up, it is going to keep reducing by m. So if suppose the bottommost layer, the leaf wala layer, suppose it had, like, the total is supposed to be n, right? So then in the next layer there will be, suppose here there was x, in the next layer there will be x by m, in the next layer again it will be x by m divided by m again, so it will keep reducing by m till we come across 1, right? So if we keep doing this, our h will actually become order of log n base m. Order of log n base m. So there are a lot of proofs also behind this, but this is the easiest way to understand, because total number of keys are n, and with every level the number of keys that can be stored are becoming m times. So height becomes the number of iterations while searching or while going through the entire tree. So that is why h becomes log of n base m, and that is what we used while figuring out the complexity for searching, inserting and deleting, right? So in our case, in the example that we had taken, it was log of 10 power 6 and the order that I said was 100. That means that every node can have maximum of 100 keys, which is easily doable in real case scenario, right? So this would essentially require just 3 IO operations, and this is from where we started. I hope now the characteristics and the main important points of B trees are completely clear. Let's discuss one more very, very interesting and cool feature about B tree. Before that, just notice something about BST. Now, if we have some particular nodes and we have to insert a new node, what happens? We compare, and the new node is inserted below the present nodes, right? So we are expanding the tree where? Towards the leaves, correct? So towards the leaves is where we add the new nodes, versus what happens in B tree is that once we have the maximum number of keys in a particular node, we are going to split it and a new node is going to be inserted on top of it. So there is a new node that is inserted, and suppose maximum that we could insert is 3, and now there is one more node. Maybe the new node will be inserted on top with one more node that can move up. So what happens in B tree is that we grow towards the root. Now, why is this so important and why is this so interesting? Because this is very, very important when it comes to multi-level indexing in databases. How? See, now today we might have 100 entries in our database. Tomorrow we might have 1,000. Day after tomorrow we might have 1 million. And as the number of entries grow or as the number of entries reduce, we want the level of indexing to change and we shouldn't have to manage that. And that is what BTree does so beautifully. See, if we have 1,000 rows or 1,000 entries, then we might need only one level of indexing. But as the number of rows will increase, as the number of entries will increase, what it will do is it will create a new node towards where? Towards the root. So that is what a new level of indexing will be created. How did we visualize multi-level indexing? Like this, right? That we keep adding the index tables. So if only this index table is required, then we are going to add it. If it is not required, then we are going to remove it, and this level of indexing is enough. So this is our disk. This is the index table for this. This is the index table for this. And it is, when it is required, when we see that the number of data entries are increasing in database, that is when we can add new level of indexing. And that is how BTrees really makes things a lot more simpler. Coming to the final part of the video, let's quickly talk about what is the difference between BTrees and B+trees. Obviously, I can go into a lot more detailing, but we will quickly understand the major differences. And if you want me to go into more details, let me know in the comments. I would love to do that. I would love to create a separate video on this. But for now, just for your basic understanding, what happens in B+trees is that there is duplicate data and it is made sure that all the data is present in the leaf nodes. All the keys are present in the leaf nodes, and then all the leaf nodes are connected in a linked list. Now, how does this help? So in database, range queries are very, very common, right? So in range queries, whenever you need like a lot of range queries, B+trees become more efficient than B-trees. Why? Because you can just traverse that, okay, from 15 till 100, give me all the keys or something like that. You can basically traverse in a linked list way, in a very easy way. Versus in a B-tree, what would happen is that you would need multiple traversals. You would have to go up and then go down like that, right? You would need multiple traversals for range queries. It won't be as straightforward. That is why, because this is such a common operation in databases, B+trees came into picture and it is very, very famous. The major difference is that in B-trees, the keys are present in the internal nodes as well. Versus in B+trees, all the keys are present in the leaf nodes. It is stored on a single file on disk. How a node of BTree is going to look like, getting the tokens. This is where my start table is going to happen. Can you see the flow? That from VDBE we called a BTree function. From BTree function we are calling a pager function. If crash happened, we would have used this journal file. List of dirty pages in LRU order. Welcome to the free course of Databases in Depth by Educosys, where we are not only going to discuss the databases in theory, but we are also going to see the code in a lot of detail. And not just see the code, but debug the most common statements like insert, create, select, and so on. It is my guarantee that this is not only the most detailed, but also the simplest and the coolest tutorial series on databases on YouTube so far. The only thing is that 77-78% of you have still not subscribed. So even though it is completely free for you, hitting that just one button is going to motivate me so much. It is going to mean to me so much, you have no idea. So if you could just take a second to hit that subscribe button and share the series with anyone who is looking to become a better software engineer, who is interested in software engineering, it would mean the world to me. Now, without wasting any time, let's get started. Have you ever wondered which databases are used to store data on your mobile phone while using mobile apps? I think all of you will agree that some data is stored on mobile phone, right? Like for cases of offline usage, or simply you cannot make network calls for anything and everything, right? You do need to store some data on the front end itself. And same is the case for IoT devices. The basic thing is that you need some lightweight database. You obviously cannot use something like MongoDB or Postgres because you require a separate server running for those databases. So what do you use in such cases in mobile apps or IoT devices? The most common solution is SQLite, and that is what this video is going to be about. We are going to see the code in detail, but before we do that, let us understand what is SQLite and why is it so famous. SQLite is lightweight embedded serverless DB. What does this mean? Lightweight meaning it has literally few hundreds of KBs of footprint. Literally 200, 300 KB is enough. Obviously, the exact value depends on the OS that you're using, but that's it. 200, 300 KB should be enough. So it is very lightweight. It is embedded. What does embedded means? So whatever app you're using, the library, the SQLite library is embeddable in the same process. So you don't need like a separate process running for SQLite. So it is lightweight, it is embeddable, and it needs zero configuration. What do I mean by zero configuration? Literally no configuration, nothing. Just download the code, the open source code. Obviously that is why we will be able to see the code. It is open source. So you can just download it. You can compile it using any C compiler and use it. There is no configuration required. Talking about some cool features, it supports ACID properties. So yes, it supports atomicity, consistency, isolation, durability. Also, if there are say power failures or system crashes, it has recovery of DB file. So we will actually look at the code at how is the data being stored on the DB file and how does this recovery happen. It is also thread safe, so it takes care of DB level thread concurrency. And also it is cross-platform. So it lets you literally move your DB file from one platform to another platform. Let's say you created your DB file in the Windows platform. You literally just have to copy, paste to a Mac platform, and it will work seamlessly. It will work identically. That is so cool, right? But out of all the features that I have talked so far, the coolest thing about SQLite is always going to be that it is one of the most simplest databases out there. Supporting so many features and still being so simple, the code is very interesting. How it is structured is going to be very, very interesting. But before we get into the details of SQLite architecture, it is very important for you to understand that databases like MySQL and Postgres are different from SQLite. Although all three of them support ACID transactions, you use SQL queries, these two are different. How? MySQL and Postgres are client-server databases. They are designed for large scale. They are designed to handle high performance, higher concurrency. So you must have seen them being commonly used in high-level system design in huge web apps like Netflix, YouTube, and so on, right? And you must have seen that we create different database server because they are designed like that. Versus what we discuss in SQLite, they are designed for small to medium applications like mobile apps, like IoT devices. They are embedded. They don't need separate process. So it is very important that you understand the difference between them. We will be discussing Postgres also in this course. But as we go ahead with SQLite, it is very important that you understand the use cases where it is a good fit. This is the SQLite open source code. This is what I will be cloning and showing you in detail. So here, as you can see, there's the source code inside this. There's ext folder where all the extensions are going to be there. There's test folder where all the test cases, scripts and all are written. So essentially our main goal is going to be to understand the source code, right? So this is what we have to understand. There's a lot of code, but the documentation of this is actually pretty awesome. I will add the links in the description, and also the official documentation page is also pretty good. So this is their official page, and if you go to the documentation, it is pretty detailed. So whatever I am explaining in this video, I have understood from this documentation. I have gone through it in detail. Even in the code, the documentation is pretty detailed. I'll be showing it to you that as we discuss each and every module and component, I will show you the documentation. I will show you the code as well. Let's get started. Let's finally get started with understanding the SQLite architecture. But to make things easier, let's get started with a quick overview, and then we will discuss this in a lot more detail and I'll show you the code. Now, to make things very simple, what we are going to do is we are going to divide this entire SQLite architecture into some components. To be precise, we will talk about 7 components and we will understand the code component by component, and then later we will stitch everything together while debugging. And to make things even more simpler, we are going to divide these components into 2 divisions. Let me explain by what I'm trying to say. So how do we talk to SQLite? How do we tell SQLite that, okay, do this, do that? We send some SQL commands, correct? Now these commands are in English. We say create table or select all from or insert into or update this or delete this. So the first thing that SQLite has to do is make sense of what we are trying to say, right? Because these commands are in English or they are in some form, right? In some particular format we are sending these commands. Now first thing that SQLite is supposed to do is make sense of these commands, and whatever instruction we are saying, generate bytecode instruction for that. So basically whatever we are trying to say, generate bytecode for that. So this is what our first division is going to be doing. What our second division is going to be doing is that it is going to receive this bytecode, and this is the division that is going to be responsible for actually doing the data processing. So we are dividing our components into two divisions. The first division is going to have 3 components. The second division is going to have 4 components. So the first division is only responsible for processing what we are trying to say and generating the bytecode. The second division is going to pick up this bytecode and actually do the data processing. Okay, let's talk about the first division of components first. So as we said, we are getting some SQL commands. Now how do these commands come? Like create table or insert into. So now this big command we are going to divide into chunks and understand that okay, create is one token, table is one token, or insert is one token, and then into is another token. So what we are doing, whatever command is coming, we are tokenizing it and understanding okay, these are the tokens that are coming. So the first component is going to be a simple tokenizer, that okay, tokenize it. Now once we tokenize this, together we are going to understand, okay, does this statement even make sense? Is this a valid statement or not? What is it trying to say? Can we optimize it further? Like if I say into insert, does it make sense? No. Or if I say table create, does it make sense? No, it doesn't. Or if I say create into, does it make sense? No. So is it a valid statement? Do these tokens together make sense? Or what is it trying to say? Can we optimize it? All of this is going to be done by our parser. So first we have tokenizer, then we have parser. And then whatever parsing we have done, after that we can finally do our code generation, and this will be done by our code generator. Now this code generator will finally generate our bytecode, and this bytecode is going to be interpreted by our second division. Now these divisions we can also call them as front end and back end, but don't get confused. This is not like a front end back end of the huge systems that we usually talk about. It is just division of the components, and because the first division, what it is doing, it is making sense of whatever we are sending. It is sort of like a front end of SQLite, and whatever are the other components, they're going to be doing the processing work, and that is why we can consider it like a back end of SQLite. But don't get confused by the terms of front end and back end, and that is why initially I use the terms divisions and not front end and back end. Now let's understand the second division or the back end of SQLite. As you must have understood by now, the first thing that this new division is supposed to do is to interpret or to implement whatever code instruction is given to us, right? So we are giving some code instruction in this bytecode. So the first component, what it is supposed to do, it is supposed to implement this. So this is the component that will actually be doing the data processing. This component is called Virtual Database Engine or VDBE, or you can also call it the VM, so which is virtual machine. So this component is essentially abstraction of a new machine altogether. This is the one that is actually doing the data processing. But what is happening over here is that this component is still viewing the data in terms of tables, rows and columns. That is how we view the data, correct? Now it is not like the data is stored in tables and columns and rows, right? Internally it is stored in some other format. But this component is still viewing the data in terms of tables and rows and columns, and the components that are below it, that is where the data is stored in some other form, and that is what we will understand now. Before I go to the next component, this is a reminder that we are going to be discussing each of these components in a lot of detail. We are going to be seeing the code, so it is going to become clearer. Just stay patient with me. It is very interesting, right? So what this virtual machine is doing is that it is just a component. It's not a different machine in the same SQLite code. It is just one small component, and what it is doing, it is actually doing the data processing. So when I show you the code, you will see that it is actually a huge switch statement. So what it is doing is that if my bytecode is saying that select something, it is going to actually do the selection. If it is saying insert, it is actually going to do the insertion. So that is where the data processing is happening. Now the components below that is where we will understand that how data is stored. So the next component that this VDB actually uses is B or B plus tree. Now there is a different video altogether where I have covered that why B plus trees are commonly used to store indexes and tables in databases. So you can refer to that video. The link is in the description. It is part of this entire free course. So what happens in SQLite is that there is a separate B plus tree for every table and every index. So there is one completely different tree for a table or for an index, correct? Now this VDBE or VM is going to use this B tree to insert or to delete or to whatever it has to do. It is going to use this B tree component. So VDBE is using this BTree component. BTree component is going to use the next component, which is going to use the next component. Now, before understanding the next two components, it is very important to understand that how data is stored on disk, because we are viewing the data in terms of BTree, that okay, one entire table. So we are visualizing it how that okay, this table corresponds to a BTree. Okay, so but then there is a lot of data inside this, right? Okay, there's data, there's data, there's data. How is it stored on disk after all? So that is what we should understand before going to the next components, and let me tell you that first. In SQLite, whatever data is there in a particular database, it is stored on a single file on disk. So there is a single file on disk corresponding to every database, and I will actually show this to you. As I create a new database, there will be a new file that will be created. Suppose I create one more database, another file, another database, another file. So if I delete the file, the database is gone. So every database is represented by a single file on disk. Now what is a file actually? File is nothing but how does it look like? So if suppose this is a file, there's just some data written on it, right? So some data that is written on it. It is just some bytes put together, correct? Some bits. So there's like a lot of data. Now what we are going to do in SQLite is that we are going to take a fixed size. So by default the size is 4 KB. We can also configure it, but for now to keep the explanation simple, I'm going to say 4 KB is the default size, it is the size. So what we are going to do is we're going to take this one file, the disk file, and we're going to divide into that fixed size chunks. So if you're taking 4 KB, just divide the entire file into 4 KB ka chunks. So what it is going to look like, okay, 4 KB, another 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 4 KB. And in SQLite, these chunks are called pages, which are represented by page numbers. So if we have to understand it in very simple terms, a single DB is represented by a single file on disk, and that is nothing but an array of pages, just some pages put together. So like page 1, page 2, page 3, page 4, page 5, like this. It is just an array of pages. And this is how your disk file looks like. Now next important thing that you need to understand is that this file is on disk, right? And the pages are within the file obviously. Now how will a processing happen? Because the disk file is huge. When you want to do some change to a particular page, right? If you want to insert something, or you want to get something, or you want to write something, it will be done to a few pages, not to the entire disk file. The disk file is huge. And whenever you have to process something, whenever you have to make changes to the file, what you're going to do is you're going to take out a few pages of it, maybe like 1 page or 2 pages. You're going to take out the page, put it into memory, like into RAM, or you can say into cache. So you're going to take those pages out that you need to be processed and put it to cache, correct? Because your DB file is on disk. Now if you want to process something, you have to take it out to memory, to RAM, correct? So you're going to take it out and use cache. So I will actually show you the code. And interestingly, if you have heard about caching even a bit, and if I ask you, do you know any one caching technique, you will probably come up with LRU, and that is what is used by SQLite. I will actually show you the code. See that SQLite is actually using LRU technique to maintain its cache, but we'll discuss it in a lot more detail. I will show it to you. But in order to understand the overview, what is happening is there is a disk file, there are pages. Now, whenever we want to process a few pages, those pages have to be taken out, put to cache, processed, and then something. Now, this processing is done by our next component, which is called pager. This pager component is actually extremely important, and we're going to spend a lot of time on it. Cache management is just one of the things it has to do. So our asset transactions happen because of pager. The rollback thing that I was talking about happens because of pager. The locking mechanism is done by pager. So all of that is taken care by pager, and we'll discuss it in a lot of detail. I know there might be a bit of confusion right now that, we were talking about BTrees and suddenly we're talking about pager. How does that happen? Let me give you some idea, and then when we talk into a lot of detail, it will be clearer. See, BTree is what a concept. So tree is what? Okay, there are nodes, right? So BTree is also in the end a tree. Now, each node in the end is stored in pager. Now, note, how is the page represented? By a page number. So our BTree component is going to say that, okay, get me this particular node, essentially what it is telling pager is get me this particular page and process it. So if we have to visualize it, the entire table, so when we say a table in SQLite, so the table is structured in a B tree, but how are those B tree nodes stored on the disk file? In the end, these are some pages. Now we have just one file, so we will see how a page looks like, how it together forms the DB file, but each page, they will be represented by a page number. Now one page can be a node corresponding to the B tree. So we will visualize it like this, we will see the code. Coming to the last component, it might be obvious to a few of you. In the end, what we have to do is we have to deal with a disk file. Now, what do we have to do when we talk about file? We perform a lot of operations on the disk file, right? We say open file or read file or close file. So I will actually show you that when I say create a new database, there is like an open statement that is called in the operating system, right? Because we are creating a file or we are opening a file, and then similarly we are closing a file. Just how we do like read, open, close, that is what is exactly happening. But since SQLite is cross-platform, we need one common interface which can say that, okay, oh, this is Windows platform. So, okay, we have to open like this. Okay, this is Mac platform. We have to close it like this, and so on and so forth. So that is what our last component does. We can call it virtual file system or VFS. You will actually see this variable being used a lot of times in the code, VFS, or you can also call it operating system interface. So it is like an interface that, okay, if this is your operating system, this is how you're going to open the file, or you're going to read the file or close the file, and so on. So these are the main 7 components that we have to understand, and we have to see the code. But you have understood the flow. So congratulations, you actually understand the overview of SQLite architecture. Now it will just become a lot more fun because we will pick up each and every component and we will see it in a lot of detail. We will see the code. And in the end, when I debug, suppose when I debug the create statement or insert statement, you will see that first Tokeniser is hit, then Parser is hit, then code generator is hit, then VM is hit, then BTree is hit, then pager is hit, then OS interface. So this is the exact order in which components or modules are called. So the basics are now clear. Let's get to the detailing. Before we move ahead, I would just like to take a minute over here to tell you that if you're preparing for interviews or if you're looking to become a better software engineer, I would love to be part of your learning journey and make it easier, faster, better, and more fun. I teach live, plus you also get access to the recordings so you can learn at your own pace, and you get a consistent teaching style because I teach all HLD, LLD, DSA, project-based courses where we cover industry-level projects like YouTube, WhatsApp, Zerotha. We cover MERN stack as well as DevOps, and we also have C++. Plus, if you sign up for any of our courses, you get lifetime access to all the batches, the past, present, future, everything. You also get access to our mock interview platform. You can come practice anytime. We are going to guide you. We obviously have doubt support as well. We are putting our heart and soul into teaching. So if interested, at least check out the site. All the detailed curriculums, the testimonials, the answers to all the general FAQ, everything is present over here. Just check it out. Educosys.com is the site. Plus, if you still have any questions, feel free to reach out to us at support@educosys.com. We will also guide you about what is better for you. At least check out the testimonials for now.
The best thing that I like about Educosys is their courses are live.
Kirti herself. The way she teaches, the way the courses are structured are actually the best part.
Their live classes and the very helpful Discord community.
I feel very confident as compared to what I was before these courses as a software engineer.
My experience at Educosys have been really great.
I feel more confident as a software engineer after enrolling in Educosys.
But for now, let's get back to the video. This is the cloned SQLite project, the same SQLite project that I showed you on GitHub. I have just cloned it and this is on my system, that's it. First, let me show you some important files so that you get used to the code structure and you understand it, how is the code written. So we are in the SRC folder and that is the folder we'll be focusing on. So let's see some important files. So here you can see there is auth.c, there is BTree files, right? So these are the files related to BTree. If you see, the documentation is just amazing. The detailing to which they have explained is just awesome. This is how I've understood the entire code. I literally went through all the files, read through the documentation. So if you see over here, like BTree end, so here they have literally shown that how a node of BTree is going to look like, what all things are going to be there inside it. So if you just go down, if you read about it, this is how a page is going to look like. So each BTree pages is divided into 3 sections. So you can see file header, page header, and see they have explained it in very awesome way. My goal is to make things simpler for you and to summarize things in as easy way as possible. And interestingly, if you see on the top of every single file, they have written this with the copyright statement: may you do good and not evil. May you find forgiveness for yourself and forgive others. May you share freely, never taking more than you can give. Okay, amazing, but okay, cool. So let's look at some very important files. So BTree files will be important for us. We will be going through them in detail. Other than that, what else will we go through in detail? So you can see there are some mutex files. So this is where our OS layer is handled. So the last layer that we just discussed, the last component. So this is the OS layer. Then you can see pager.c, pager.h, again very, very important files. So here you can see interface.SQLite page cache subsystem, right? And here you can see this is like the cache files. Then we will be covering in a lot of detail what exactly is SQLite 3 file. It is extremely important. It is the most important file of the project, and I will tell you how it is generated, what it is in detail. Just give me some time for that. There is table file, then there are some test files. And after that you can see tokenized file is from where we will start. We will start understanding tokenization. Then you can see update.c, absurd.c. See, you remember VDBE component, the virtual machine component. So this is the header file for virtual database engine. So I told you, right, VDBE component. So that entire code is in these 2 files. Then other than that, VDBE trace, vtab. So these are the important files that we will be going through. There is utility file and so on. So let's get started with tokenized.c and let's understand the main functions that are hit while tokenization. In tokenized.c, the most important function that is going to be hit like so many times, we will be just done with this function, it will be hit so many times, is SQLite 3 run parser. So what is happening over here is that we will get the entire SQL string that we will be passing. So like select all or insert into or create space table. And this is where the entire parsing is going to happen. So if we go inside this, so don't get overwhelmed by the lot of code. So if you see inside this, there is a very simple while statement. There's a while one statement. So does it go on forever? Of course not. We will see. So first of all, they are getting the tokens. So one by one in every loop, they will get the token like create space table. So first they will get the token create, then they will get the token space, then they will get the token table like this. And if you see for every token type, there is like sort of a switch statement over here. Let me show you what exactly is happening. Now you can see there are different token types, right? Space, over, filter. We will see what it is. First, let's see what is happening in get token. So if we go over here, it is returning the length of the token that begins at that point. So here you can see again there is CC space, CC minus, CC LP. There is something happening over here. So let's see what is CC space. So it is nothing but a character class. So we are just figuring out whatever character that we are dealing with. Is it a digit? Is it a dollar? Is it a minus? Or is it a slash? Is it a comma? Is it and? So, or is it illegal? Right? So we're just figuring out that whatever we are dealing with, what token is it, right? So this is where we are figuring out that what is the character that we have gotten. Accordingly, we are assigning a token type. So what is a token type? Now see, token type can be, for example, it can be table or it can be create. So you figure out that, okay, these characters together are forming this token. So create or table. So essentially when the parsing is going to happen, and I will show you this literally when we debug, that when we do create space table, we will see that the tokens that are identified will be say 17, then there will be a token for space. So if I search tk underscore space, so you can see there is 184, okay. So there will be like 17, then 184, then create space, and then there will be table, so it will be 16. So we will see like this that parsing is happening and we can figure out that these are the tokens. Now corresponding to each token, there will be like a function called. So this is exactly where those things are happening, right? So this is where we are getting the tokens. So as you can see, this is literally a huge switch statement, right? Is it CC pipe? Is it comma? Is it and? So you're just assigning a token type to it. Okay, and let's get back to our parser. So now that you have a fair idea, rough idea of exactly how tokenization is happening, we're just basically going through every character by character and then putting some valid characters together and saying that, okay, this is a keyword, this is a token. Now we have tokens, and now we should understand a bit about how exactly parsing is happening, right? So after tokenizer, there is parser. So let's look at a very, very important file, which is parse.y. Now you would be thinking that, Kirti, parse.c and h makes sense. What is .y file? Now let me explain to you. So if you know a bit about Parser generator, this will be easier. If you don't, it's fine. Let me just tell you in very simple terms. So earlier there were some Parser generators named YACC and Python. Now SQLite has written their own Parser generator, which is called Lemon, which is more easier, it is simpler. So this file contains SQLite's SQL parser in very simple terms. Now what is happening inside this? What does this file look like? Now I will make it very, very simple. Just look at this one statement. So look at this statement. Suppose this is where we are saying the create table statement parser generator is there. What does it mean? See, what exactly happens in parsing? We say that, okay, these are the tokens. Now we should know that these tokens should come exactly in this order, right? Because table create and create table are different orders. So there are some rules corresponding to it. So if these tokens are coming in this order, if they're following these particular grammar rules, then we can call this function or we can take this action. This is exactly what is happening in parsing, right? That if I have tokens which are following this particular grammar rule, call so and so function or perform this particular action. That is exactly what is happening. See, here we are saying that this is the grammar rule in very simple terms, and we are saying that call this particular function. Okay, and what is happening inside this function? So if you see SQLite 3 start table, if I just search for this, this is what is happening over here. So if you see, this is where it is telling, see, this is where parsing will be happening, and this is where we will tell that, okay, these were the tokens that were sent and this is the function that we have to call. So if I go inside this, particular function, you can see this is where my start table is going to happen. So there is a parser generator which is going to say, see, if tokens are coming in this order, then you call this particular function, which is this start table function, and this is where our, we will begin constructing a new table. So if you see like this, there will be all the statements. So like this was for start table, right? This will be similarly. So if we want to see more statements, let's see. So you can see create view statement, the drop table statement, then select statement. So see, select query should look like this, and after that you will call SQLite 3 select. Like this, we can keep going through a lot of statements in detail, but for now, to summarize it in a very simple terms, we first saw tokenization. What is tokenization? You take the SQL query that is coming, you divide into tokens, and then parsing, what is happening? So yeah, we have a parse generator which makes sense of these tokens put together, that okay, this is the action that has to be performed. Like for example, we saw that start table is one action that has to be performed. So if we come to start table over here, and if we go down, see, there are a bunch of things that are happening over here, and I will explain this to you. We will debug this also, so just stay with me. So first thing, we are reading schema. This is one crucial thing. I will explain you why it is crucial. And other than this, if you go down, you will see there are a lot of VDBE calls that are happening, right? So what was the order in which the components were called? There was tokenizer, then there was parser. Then before VDB, there should be one more thing, right? Which is what? Which is code generator. So we have to make sure that whatever we are sending to VDB actually makes sense. It is bytecode. So first, let me tell you exactly where that happens, and then we can see that how the call to that bytecode generator is happening. Let us go through that first. So for that, one very important file is prepare.c. If we come over here, so see, if we go to the file, this file contains the implementation of SQLite 3 prepare interface and routines that contribute to loading the DB schema from disk. Okay, and the most important structure is SQLite 3 prepare. And if we go to this statement, so let me actually just go to this. So here, okay, let's go to this. This is very, very important. An instance of this object represents a single SQL statement. So whatever statement is there, like create table, insert into, select all, that has been compiled into binary form. So this is the binary code that we are generating and we are sending to the VDBE or VM. So this is the SQL statement compiled into binary form and it is ready to be evaluated. Think of each SQL statement as a separate computer program. The original SQL text is the source code. So this is exactly what our first division of components were doing, right? The front end. What was it doing? It is just making sense of whatever SQL statement has come to us. And what is the final output? The output is this SQL3 statement. A prepared statement object is the compiled object code. All SQL must be converted into prepared statement before it can be run. Who is going to start running it? The first component is going to be VDBE or VM. The life cycle of a prepared statement object usually goes like this. Create the prepared statement object using this prepare v2. So this seems like a very important function, right? So we'll see SQLite 3 prepare v2. Bind values to the parameters. So this will just say, okay, this is the meaning of this statement. Then we have to bind the values. Like for example, if table name is there, then we have to say, okay, this is the table name. And then we are going to run. So the running of the SQL is happening where? In SQLite 3 step. So these are the very important functions, SQLite 3 prepare to, SQLite 3 step. And once it happens, after that SQLite 3 reset is called, but destroying the object is happening in SQLite 3 finalize. So any statement that is being called has to go through these three very, very important functions that we should understand: prepare v2, step, and finalize. So every time a particular statement is called, we have to see that these three functions are called or not, and it should be in this order. First we have to prepare the statement, then we have to execute the statement. This is where the running is happening, and this is where we are destroying the object. That okay, it has been run now you can destroy. Now that we have a rough idea that this is how binary form of the SQL statement is generated, let's quickly go through the order once more. So first thing that we saw was that tokenization happens. That was in parser, right? First was get token. So we generated the tokens. Then we saw that okay, there's a parser generator and it says that okay, if this is the grammar rules, call this function. What was that function? So let's take the example of create table itself. So when we create table, it goes and calls this function, right? Start table. So this is what it pointed to, the parser. Now that it has pointed to this, I told you that one very important function inside this is read schema, and let's see why it is so important and why do we need to read schema. So when we say create table, so we are understanding the flow of create table right now, so focus on that. So when we say create table, first thing that we need to make sure is that the new table name should not collide with an existing index or table name. Because if I am creating a new table, there should not be an existing table or index with the same name. So you can see here I am reading the schema, and then whatever is there, I am going to say find the table with this name. Is it there? If it is there, then I am going to return the error from here itself. See error message. That table already exists. Maybe there is a view, maybe there is a table, maybe it already exists, right? So let's see what exactly is happening inside this read schema. So if I go inside this read schema, there is a mutex that is being held, and there are a lot of things that are going to happen. I'm going to talk about the most important things. So there is one init function, and if we go further inside this, there is one init1 function. See, there are a lot of things that are going to happen. So there is one in-memory representation of schema tables that are created. We will talk about this in detail. But for now, what is most important thing for you to understand is exec. So if I go inside this particular function, see over here, this is what is called from initialize. And if you see, this is where you will be able to see the statements being called. See, first one is SQLite 3 prepare v2. This is where you are preparing the statement. Then this is where you are executing the statement. Here you should be able to see a step call. Where is it? Where is it? So yes, so this is the step call, right? So first call was the prepare call. Then there is a step call. And after that, we should be able to see a finalize call. So see, there's a finalize call. So this was the order which we saw also. But now you can see that how and exactly where it is happening. So inside the exec, so if you see, this is the function that is responsible for executing the SQL code. Whatever SQL code we had, we first tokenized it, we passed it, then we say, okay, start table. Now while initializing the table, we are saying, okay, execute the statements. First prepare the statement. That means prepare the binary form of whatever the SQL statement was given to us. Then what you are going to do, then you are going to execute the statement and then you can destroy it. So when we say finalize, if we go inside this, you can see clean up and delete the VDBE after execution. Now, clean up and delete the VDBE after execution, where did VDBE come into picture? Okay, so we are finally leveling up because we are talking about VDBE, which is in the backend or the core of SQLite, correct? Before I move ahead, let me just quickly remind you that this video is not supposed to be easy. You're talking about internals of a database. It is one of the coolest things as a software engineer, right? You will feel very proud, and if you tell anyone, it is like so cool that you understood internals of a database. It is not supposed to be easy. So I am just talking about the main functions right now. But the more you go through this video again and again, and also when you see the debugging video, the next video, things will become just so much more easier. So stay patient. I do not want you to leave the video right now because it doesn't make sense leaving till here, because we talked about the first division. We talked about the front end of SQLite. We are finally getting to the core, the back end. So it doesn't make sense that you leave right now. So don't leave, okay? Stay till the end of the video. Let's understand what is happening in VDBE. Why did we get into VDBE suddenly? To understand, let's quickly go to the start of the file and see what's written. So it's written that this file contains code used for creating, destroying and populating a VDBE or an SQLite 3 statement as it is known to the outside world. What does that mean? That means that VDBE and SQLite 3 statement are actually the same thing. It is just that when we talk about the front end, when we talk in the first division of components, we refer to it as SQLite 3 statement. And when we come to the back end, the same thing is VDBE. See, VDBE or VM is a simple component. What it is supposed to do, it is just supposed to execute some instructions. Now those instructions are in binary form, are in bytecode. You're just supposed to execute it. So let me just show you this. Let me make things much more clear. So if we go back to where we called SQLite 3 VDBE finalize, which was our exec statement, right? So inside this, there was all the prepare, v2, step and the finalize calls. So if I go back again in this step function, now let me show you something very interesting. Can you see this? What does this mean? We are typecasting over here, right? So actually the VDBE and the statement that is there is exactly the same thing. It is just that in the front end and the back end, the different terms are used. And if you see this, this is there in all the functions over here. So let me actually show you. We are in VDBE API right now. So if I show you, you will be able to see this in a lot of functions. So can you see this over here? SQLite 3 reset. So same thing is happening over here, correct? Let's see. We'll be able to see it in more places, I'm pretty sure. Let me actually search these statements so that it will be easier. See, it is happening in step, it is happening in statement explain, in statement busy, in finalize. So you will see this happening in a lot of places, not just in this file, in other files as well. That statement is being converted to VDBE. This actually proves my understanding that statement and VDBE are essentially the same thing. I think it's finally time to see that how VDBE or VM executes whatever bytecode we have, whatever prepared statement we have, how does it execute? So how normal machines use assembly language? There is one language that is very specific to SQLite VDBE. You are not supposed to know it. It will not run anywhere outside. Even SQLite people say that it's specific to VDBE and you're not supposed to run it, not even the front end. It is specific to the core. So let's see what exactly happens. First, let's see the VDBE structure. So if we go inside this, this is how the structure looks like, right? So over here, you can see linked list of VDBEs with the same VDBE.db. Now here you can see something called op, space to hold the virtual machines program. And if you go back, one very important structure that you're going to see is VDBE op. Let me just show that to you, VDBE op. So yes, let us go into this, and this is very important. So if you see over here, there is one opcode and then there are some operands. So this in very simple terms is the operation that VDBE is supposed to perform, and these are the operands. So suppose, in very simple terms, suppose I have to do 2 plus 5. So 2 and 5 are the operands, and the addition, the plus, is the operation that we have to perform. So you can think of it like this, that whatever VDB or the virtual machine is supposed to do, it is in the end some instructions that do this, do this, do this, do this, right? So every single instruction of the VM has an opcode and as many as 3 operands. So there can be max 3 operands. So most of the operations use, I think, 2 operands only. So there is one more that is used in some operations. The instruction is recorded as an instance of the following structure. So this is the operation that you have to perform, and these are the operands. Now you're thinking that, Kirti, where does all of this happen? So if we see the VDBE code, okay, if we see this, so do you see the switch statement? Let's see how big is the switch statement. And what is the switch on? The switch is on one opcode. So one, if you see, this is a massive switch statement where each case implements a separate instruction in the VM, right? This is in VDBE.c. And if I show you how big is the switch statement, 972 to 9055. That is how big one switch statement is. In actual simple terms, VDB is nothing but a simple switch statement. Oh, this is the instruction to be run, I will run this, and this is how I am going to run it. So it doesn't do any optimization, nothing. It just has its own language in which it is going to implement a particular operation. So if you see over here, this is the switch statement, op go to. If we see this, so these are the operations that are possible, like go to or if not, right? So these are the operations that are possible. So based on these operations, so you can see there are so many operations, right? So based on each of these operations, there is one, like correspondingly, there's a case in the switch statement. So you can see this, right? So if I close this, there's another case for go sub, there's another case. So it is also showing that, see, this is the operation that you are supposed to do. This is how it is going to look like. Write the current address to the registered. So if it is go to, what you're supposed to do, you're supposed to do jump. This is the operand return. This is the, so there is proper documentation also that how this is done. So what is happening is that whatever bytecode was there in the prepared statement, now that is like divided into small instructions. So each opcode instruction, and then it is run slowly inside the switch statement that, okay, this is what we're supposed to do. So you will actually see this being run a lot. OP halt, that means stop it. So VDB halt, that internally calls OP halt. It means stop it. Then integer 6. So you can see these are all the switch case statements, right? And this switch is inside what? It is inside VDB exec, I think. So if I just search, yes. So this is the exec statement. And if we go inside this, this is where it starts, correct? So this is happening inside VDB exec. And if we see what is happening inside exec, so execute as much as of VDB program as we can. This is the core of SQLite 3 step. So SQLite 3 step is internally calling VDB exec. So now the flow is a bit clearer that, so when we have SQLite 3 prepare, so we are preparing the statement, then when we execute, what is it calling internally? The VDB exec. So that is where we are actually executing the statements, right? So if we want to see this, so if we go inside this and see where all this is being called, actually let's see where all is this being called. Let's see where is this called from. So this, if you can see, this is called from the SQLite 3 step. So inside step, what is being called? The exec statement, and this is how execution happens. And you will see this while debugging that first we prepared, then while execution, what are we calling internally? The VDB exec. So now we have moved from front end to back end, and now VDB execution is going to happen. Since we are now discussing the backend part of SQLite, the core features, each of the components are going to be pretty huge, especially pager. It itself has so many things to be done. BTree also can be a huge discussion in itself. So what we are going to do is, to make things simple, let's first make sure that we are able to visualize the entire flow of components. In the component diagram that we had discussed in the SQLite architecture in the beginning, what did we see? That VDB uses BTree, uses pager, and then below that there is the OS layer. So at least if we are able to see this flow happening in the code, we will have some confidence, and then we can see each of these components in a lot more detail. correct? So for that, let me just open one very important function for you. So VDBE logs, if we see VDBE commit, this is a very important function. So if we see whenever changes have to be made to DB, we usually say that we are committing the changes, right, to the disk. So if we see in VDBE commit, inside this, you will see there are a lot of BTree calls that were going to happen, like BTree enter, right? But the most important two calls that you should be thinking about is BTree commit phase 1 and BTree commit phase 2. We will discuss in a lot of detail that what is phase 1, what is phase 2. But to give you a quick context, do you remember in the starting we discussed that the entire DB file is on disk. Now we bring up a few pages on memory and then we make changes in the memory and then we push to the disk. Now what you should be thinking about right now is that what if DB crashes in between, because we are making the changes on memory, right? How do we make sure that the entire changes go to the disk, and in cases of crashing and all, how do we support recovery? So in order to all of this, we will understand phase 1, phase 2 properly, that how is this happening. This is a very common solution also in all the databases, not only in SQLite. We will talk about this in detail, but just notice that there are two things that are written over here, phase 1 and phase 2. So VDB internally is calling a BTree call, right? BTree commit phase 1, BTree commit phase 2. If I go inside this, if I go inside BTree commit phase 1, see internally it is calling pager commit phase 1. So can you see the flow that from VDBE we called a BTree function, from BTree function we are calling a pager function. So the component flow is happening like that. Similarly, if I go to BTree commit phase 2, if I go inside this, see from BTree commit phase 2 we are calling pager phase 2. So at least that flow should be completely clear now. From the starting, first we tokenize, then we parse, then we generate bytecode. Bytecode, we prepare the statement, which is nothing but a VDB pointer itself. Then VDB internally uses BTree, BTree uses pager. Now beneath pager, what will be the last layer? The OS layer. Now that you have understood this, let's see that finally how the data is stored on disk, how things are happening. Let's understand in a lot more detail. Since we just saw in the code that the commit happens in two phases, phase 1 and phase 2, it is time that we discuss that why SQLite does it in two phases and how does it actually happen. This will introduce us to a new concept which is not just applicable for SQLite, but a lot of databases use it. So this is pretty important. Listen very carefully. So what did we discuss in the starting? That SQLite supports ACID transactions, right? What does A stand for in ACID? It is atomicity. What does atomicity mean? In very simple terms, a transaction should either completely happen or it should not happen at all. It should not happen that a few steps of the transaction happen and the others did not happen. So a very common example that everyone gives, that I also give, is suppose there are two people, A and B, and 100 rupees need to be transferred from A to B. So there are two steps over here, that 100 rupees should be deducted from A and 100 rupees should be given to B. It should be incremented in B's account. So there are two steps over here. It should never happen that the money got deducted from A, but it never reached B. And it should also never happen that the money got incremented for B, but it never got deducted for A. Because both of these scenarios can be disastrous. We need to make sure that the transaction either completely happens or it does not happen. Now let's discuss that what did we see in SQLite. What happens is that there is a disk file, and whenever we want to make some changes to it, we bring the pages to memory. So in this example, suppose we have to make the transaction from A to B. Suppose there are two pages where this data is there, and we bring the pages to memory and we update the values for A and B. So we did the transaction that minus 100 plus 100 in memory. Now what happened was that while we were putting these changes back to the disk file, maybe we decremented for A, we had not incremented for B. So just we did this and then entire crash happened, and maybe the disk file crashed or memory crashed or whatever crashed happened. So in case of crash, what do we do now? So now when the disk file comes back up, it will have no idea. So it would have the data that A was deducted, but B did not get the money. So what is going to happen now? This is not the expected behavior. We expect what? We expect atomicity from SQLite. So how should SQLite take this into picture? How does it handle this scenario? So to handle this scenario, there is one more component that finally comes into picture, which is called journal. So there are three things. One is the cache, one is the journal, and the other is the disk file. So let's see what exactly happens in phase 1 and phase 2. As you can see here, I have opened the documentation for commit phase 1, BTree commit phase 1, and let's see what it is saying. Okay, so this routine does the first phase of two-phase commit. So there are two phases, right? Phase 1 and phase 2. So let's quickly write that down. So commit phase 1 and phase 2. So what happens in phase 1? This routine causes a rollback journal to be created. So we are creating the journal. Okay, so create journal is what is happening over here. And if it does not already exist, and populate it with enough information so that if a power loss occurs, the DB can be restored to its original state by playing back the journal. So this has the original state. So when we load the pages to memory, what we do is whatever is the original state, that is pushed to journal. Okay, so that in case power loss occurs, so in case the crash happens, so if crash happens, so there is the original file that is there over here. So your disk file can always roll back to journal because the original part is already there, right? So what are we doing? If a power loss occurs, the DB can be restored to its original state by playing back the journal. That means that the original data, the original state is in journal, you can put it back to your disk file. This is also called rollback. This is called rollback. So what is rollback? That you're rolling back to the original state. There is also something called writing ahead. That means that you are making the changes. So in this case, I'm talking about rolling back. Then the contents of the journal are flushed to the disk. So when we say flush to the disk, we do not mean disk file over here. Don't get confused. So this journal initially also, obviously, whenever you make any changes, you are making it in memory. So what you're doing is you push the journal to disk. So we are pushing the journal to disk. And I will actually show this to you while debugging, that there is a journal file that is created, and you will be able to see that, okay, a new journal file got created right now because we are making the changes. After the journal is safely on Oxide, that means it is safely on the disk, the changes to the DB are returned into the DB file and flushed to Oxide. So you make the changes over here and then push to your DB. At the end of this call, the rollback journal still exists on the disk. So after this phase, that is after commit phase 1, journal file is still there on disk. Okay, it is still there on disk. The journal still exists on disk and we are still holding all the logs. So logs are there. The transaction has not committed. So after this, there happens commit phase 2 for the second phase of the commit process. Let's see what is happening in the phase 2. So commit the transaction currently in progress. So you can say this is the phase 2. Let's see what is written. This routine implements the second phase of the two-phase commit. So phase 1 does the first phase and should be invoked prior to calling this routine. So it is specifically mentioning that first phase and then second phase. First phase did what? Did all the work of writing information out to the disk and flushing all the contents so that they are written on the disk platter. So you made sure that the changes are done in memory and you made sure that they are put to the disk as well. All this routine has to do is to delete or truncate or zero the header in the rollback journal, which causes the transaction to commit and drop logs. So it is saying that this journal file that you created, dude, now you can delete it. Now it is not needed. See, if crash happened, we would have used this journal file. But now because there is no crash, we are talking about happy flow right now. We have nicely put the changes to the disk file. After we have done that, we can delete the journal. So that is what we are doing over here. All this routine has to do is to delete or truncate or zero the header in the rollback journal. So this is the rollback journal, right? In case crash would have happened, what would have happened when SQLite would have come up? It would have seen, oh, there are some changes in the journal, or the state of the journal and the state of the disk file is not the same. So either rollback can happen, so the original thing are there in journal, right? Maybe A was deducted and B was not there. So half changes are there in the disk file. So what SQLite will do is, it will see the original state in the journal and the disk file will roll back to the original state. So this is how we can handle crashes, correct? So normally if an error occurs while the pager layer is attempting to finalize the underlying journal layer, this function returns an error and the upper layer will attempt to roll back. However, if the second argument is non-zero, so this is like very code level, so I don't think we need to know this. This will release the write lock on the DB file. If there are no active users, it also releases the read lock. So this is very, very important to understand that there are three components. One is disk file, one is memory, which is the cache, and one is journal. For revision purposes and better understanding, I've also created notes which are available for free. I'll be adding them to Educosys. I'll be refining them a bit more and I'll be adding them to Educosys. You can check out, the link is in the description. So I've summarized it in very easy way. See, in SQLite, there are, how does the update actually happen? So there are three things, right? One is cache, then there is journal, then there is the DB file, correct? So what exactly happens and how does it actually happen? Let's see. So cache is where the pages of the DB file are temporarily stored and modified in memory. So it is in RAM. By the way, don't get confused between this cache and the OS wala cache, because this is specific to SQLite. Okay. When a transaction is initiated, the necessary pages are loaded into the cache and any changes are made here first. In journal, what happens? Before any changes in the cache are returned to the DB file, a record of the original pages is written to the journal that we saw so that we can roll back. This ensures that if an error occurs, the changes can be undone, maintaining atomicity. This is what you need to understand. The DB file, once all the changes are safely recorded in the journal, the modified pages from the cache are returned to the DB file. This is the final step to make the transaction permanent. And this is where phase 1 ends. And in the phase 2, what do? You delete your journal, right? So the pager is the component that manages all three. It handles loading and modifying pages in the cache. It writes the original pages to the journal before any changes are made, ensuring that it can roll back if needed. It manages the final writing of modified pages from cache to DB file, ensuring data consistency and durability. So all of this is managed by whom? It is managed by pager, right? So this is how we are ensuring atomicity in SQLite. For reference, I have added simple notes for journal management as well. So a journal is a repository of info that is used to recover a DB when aborting a transaction or statement subtransaction, and also when recovering after an application, system or power failure. So it uses a single journal file per DB. So how there is a single disk file, there is also a single journal file per DB. It assures only rollback, undo and not redo of transactions. By the way, we will also cover that what all things are not supported in SQLite so that you have a basic understanding, because SQLite is designed to be simple and easy, correct? And the journal file is often called the rollback journal. The journal always resides in the same directory as the DB file does and has the same name with -journal appended. So I will actually show this journal file being created to you. SQLite permits at most one write transaction on a DB file at a time. It creates the journal file on the fly for every write transaction. So for every write transaction, it is created and deletes the file after the transaction is complete. So we saw phase 2, right? So that is when it is deleted. So this is called write ahead logging. I told you, right? This concept is not used just by SQLite but by many DBs, and we'll see this in future as well, to ensure durability of DB changes and recoverability of DBs and occurrences of application, system or power failures. Writing log records in the journal is lazy. SQLite does not force them to disk surface immediately. However, when before writing the next page to the DB file, it forces, so this is called flushing the journal. So flushing the journal means writing to the DB file. I told you, right, that first you make changes in the memory and then you flush them to the disk. So whenever you make changes from memory to disk, often the term that is used is flushing. Now that we have covered some really interesting theory about journaling, about caching, let's see some really interesting code as well. I'm sure you must be wondering that how does cache management happen in SQLite, right? So let's get to some really interesting code now. So here there is pager commit phase 1. Let's go inside this and let's see exactly what is happening over here. So firstly, we can see that pager flush on commit is happening and all of that. That's fine. Here can you see cache dirty list? What do we mean by cache dirty list? Let's go inside this. And if we see return a list of all dirty pages in the cache sorted by page number. What do you mean by dirty pages? So dirty pages in the cache meaning that we have made changes to these pages in the cache, but the state is different from the disk file. So when you have made some changes in the cache, but the changes are not made on the disk, these pages in the cache are called dirty pages. And let's see how they are managed, because there's a list of dirty pages, right? So let me show you something very, very interesting. Can you all see this? This is pcache, and if you see list of dirty pages in LRU order. So if you have ever heard of cache management, if you have ever read about it, either DSA, LLD, you must have come across a question of LRU caching, correct? And this is how SQLite also caches. It uses LRU order, and this is how it keeps the list of dirty pages. Let's see exactly what is happening. A complete page cache is an instance of this structure. Every entry in the cache holds a single page of the DB file. The BTree layer only operates on the cached copy of DB pages. Remember, I told you BTree component uses pager. So BTree doesn't talk to the disk file. Which component talks to the disk file? The OS. Above that there is pager. So BTree only operates on the cached copy. The page cache entry is clean if it exactly matches what is currently on disk. A page is dirty if it has been modified and needs to be persisted to disk. This is important. If it has been modified, if it needs to be persisted on disk, that is called a dirty page. And it has all the states, so dirty pages are linked to doubly linked list. So you can see PG header, so that is the header, there is next and there is previous. So this, you can actually see the entire implementation of linked list over here. So if we go through the function, see linked list management, the entire linked list code you can actually see manage dirty list. So you can see next and previous. If you do DSA, this is going to really excite you, because all of you keep saying, where do we see DSA in real code? See, this is database code. This is awesome, right? There is another function for number of cache pages. And then this is where you initialize the cache. So you can see you are making some configurations. Then there is shutdown. Then there is page size. Create a new page cache object. So there's like the another object. Set page cache size. Then there is cache fetch. So there are a lot of functions over here. Obviously, this is like too much detailing. I cannot cover everything in this video, but this is just awesome, right? This is awesome. You have to agree. So if you also want to see PG header, so this is how it looks like. Every page in the cache is controlled by an instance of the following structure. So the linked list, so this is like a node in the linked list in simple terms. You can see this is the cache object page handle, and you can also see dirty next, dirty previous, number of users of this page, next element in the list of dirty pages, previous element in the list of dirty pages. So it's like the node of the doubly linked list, right? So you can go through this code. This is pretty awesome. As you must have understood by now, one of the most important components of SQLite architecture is pager. It does so many things that understanding pager itself can be divided into some modules. So I thought let's make a small diagram of that so that this will give you further clarity of exactly what all things are being managed by pager. So what did we discuss? That there is a component on top for B or B plus trees. Then there is the pager component. So let's visualize our pager component properly now. And below pager component is what? There is the OS layer, correct? So this is going to call the pager component, and the pager component, below the pager component there is the OS layer. So now what all things does pager component do? So first of all, there is page cache, because it does cache management, right? So this is like the most important thing. And in the OS layer we do interaction with the DB file. So we can have like this, we can visualize it like this. Other than this, pager is responsible for taking care of our asset transactions. So we can say that it is also like a transaction manager. It is playing the role of a transaction manager for us, correct? Then it also plays the role of log manager, because it is the pager that takes the logs over DB. So all the read-write logs that we take, whatever read-write logs that we take, you will be able to see that it happens in the pager component. Other than this, it also plays the role of a log manager. Now, what is a log manager? We discussed about journaling, right? So we have a journal file over here. We talked about write-ahead logging, right? That is what? That is called log management. So it is also playing the role of a log manager. So if you see that pager itself takes care of transactions, it takes care of logs, it takes care of cache management, it takes care of log management. So there are so many things that Pager does. It's time that we get into the code of Page and really understand it in a lot more detail. I have now opened the official documentation of SQLite because honestly it is just pretty awesome and it is very easy to understand as well. I have gone through a lot of it, and obviously the more you read, the more you will understand. Let's look at the most important point. So here you can see that they are talking about the DB file. So the complete state of SQLite DB is usually contained in a single file on disk, as we know, which is called the main DB file. During a transaction, so when a transaction is happening, SQLite stores additional info in a second file called rollback journal, as we know. So they have also explained about write-ahead logging in a lot of detail, how it happens, what is concurrency, how they handle concurrency, what is rollback, so how the crash handling happens. So you can read the documentation in a lot of detail. What I wanted to focus on right now is on the pages. See, the main DB file consists of one or more pages. We had visualized it in the starting, right, that there's a disk file and then it is divided into small pages. See, all pages within the same DB are the same size, right? So they are of the same size. The numbering starts with 1. So the maximum size, and they have mentioned all of this. But the main thing, okay, that you should understand right now, that at any point in time, every page in the main DB has a single use, which is one of the following. So every page in your disk file is one of these types. It is either a BTree page or a free list page or a overflow page or a pointer map page or a log byte page. So these are the only types of pages that are possible. Let's understand them in detail. So what is a BTree page? Now see, BTrees can be representing like a table or an index. So it can be either a table interior page or a table leaf page. Similarly, it can be an either index interior page or index leaf page, right? Why they are important? Because see, interior, so the root also is interior, by the way. So leaves are different and then interiors are different. Then free list page means currently unused. It can be used. Either all the pages are active, free list is not active. Then we have payload overflow page. What does this mean? Why is it needed? See, because page is of fixed size, sometimes what happens is if the payload is huge and it cannot come within one page, then for that we have payload overflow pages. This is an interesting thing, right? Because sometimes the payload can be huge. If it doesn't come within one page, then what? So that is why there are overflow pages. There is pointer map page, log byte page and all of that. So this about pages is very interesting because when we see the code, you can actually see, okay, this is a BTree page, this is a free list page and so on. So understanding this really helps a lot. Now coming to the DB file, the file itself, we will actually see the file and it has a format. So what happens is that the first 100 bytes of the DB file comprise the DB file header. Now this header is divided into fields. I will actually open the DB file and show you the first 100 bytes. You will be actually able to see that first it will say SQLite format 3. You will be able to see it that the top is ODAT. Then it will say the write version, the read version, everything. So the first 100 bytes, and it is given so nicely that see first 16 bytes will be this, then from 16th byte for size 2, this is what will be there, from 18th byte, from 19th byte. So for the 100 bytes, it is given so properly, right? And they have given what is the page size, file format, version numbers. So they explained everything in a lot of detail. So obviously this is like too much detailing. We cannot discuss in that level, but I hope you get some idea. See, what are BTree pages for this also? How does it look like? So again, for that, what is the header format? It is mentioned. You will be able to see this again. Then what is a leaf cell? What is interior cell? Again, it is mentioned over here. What is a pointer map? What is cell payload? What are overflow pages, right? So going into that much detailing is obviously not possible, but the main things you should be able to understand. And I hope now you understand that how SQL table is represented. See this. Each ordinary SQL table in the DB schema is represented on disk by a table BTree. So each table has its own BTree, right? Each entry in the table BTree corresponds to a row of the SQL table. The row ID of the SQL table is the 64-bit signed integer for each entry in the table BTree. The content of each table row is stored in the DB file by first combining the values of the various columns. This is fine. Then there's primary key and all of this, right? Representation. Another important thing to see, storage of SQL database schema. So what happens whenever we create a table, there is one special table that is created, SQL schema, and we will see this table being created. When we create a table, this schema will be created. Why? You remember we read the schema and see whether there is a table that already exists with this name or with this schema or something like that. So that read schema, what are we doing? We are actually reading this schema. So when we create table internally, when I actually debug and show you, just create table internally, there are like around 8 to 9 SQL statements that get run. So you will see that the SQL run parser statement that we saw, that will be called like 8 to 9 times. That is why that is like a completely different video altogether, because within one create table statement, 8 to 9 times we will parse every statement. We will see exactly what is happening, because there will be a lot of things that we will be doing internally. We will be creating the SQLite schema, right? So we'll be talking about virtual tables and things like that. So there is alternate names. So there is SQLite master, there is SQLite temp schema, there is SQLite temp master. So you will actually see SQLite master and temp master. We will see this properly, right? So this gives you a rough idea of how things are stored internally. Considering how important Pager is, we should definitely look at the code quickly. So you can see pager.c. This is the implementation of the page cache subsystem. Pager is used to access the DB disk file, right? It implements atomic commit and rollback through the use of a journal file that is separate from the DB file. The pager also implements file locking to prevent two processes from writing the same DB file simultaneously. Now this is very, very important to understand. Firstly, as we discussed, pager acts like what? Transaction manager. So it helps us with atomic commit or rollback. And because it is also doing journaling, it is also acting like a log manager. Now this statement is helping us understand that it is also acting like a lock manager. Why lock manager? See, firstly you need to understand that it implements lock on the entire DB file. Not on a table, not on a row of table, but on entire DB file. And when does it implement the lock? It prevents two processes from writing the same DB file or from reading the DB while another is writing. That means that while one process is writing the DB file, no other process can write or read. So write log is exclusive. I am repeating this. This is very, very important to understand. What pager does is it locks the entire DB file. So what we are doing is when one process is writing to the DB file, no other process can read or write. So the lock is exclusive. So our pager is acting like a lock manager, like a log manager, like a transaction manager. And here they have also explained the design of the pager, just how we saw how the header looks and all of that, right? So if you go down, you'll be able to see that. And also the state is also given very nicely. So the states of the pager can be open, reader, so writer, logged, writer, cache mod, writer, DB mod. And they have also explained that from which state can you transition to which state, like from open to reader, reader to open, reader to write, log. And how does it happen? So it starts in this state. And then what happens? See, I can create like a separate video altogether covering just about the pager. And let me know if this would be something that you would be interested in. I thought this is a very good overview. But if you want me to go into detailing of each of these components, I can actually do that. We have a lot of more databases coming up and I would love feedback because this is like an entire series. Are you enjoying? If you would like me to go into more detailing for any particular component, let me know. I would love to do that. So here you can see the different states that are possible, how the lock is happening, right? So the locking states. So no lock shared, lock reserved, lock exclusive lock. So exactly when which lock happens. So that is also mentioned, right? That when error happens, when you can actually let it go, when exclusive lock happens, when shared lock happens. So it is just awesome. Again, I can go on about this. So one more thing I want to show before we end the video. So this file is obviously huge. This is about the pager because pager is like the most important part, right? Here you can actually see the code for moving the pages, how the journal management is happening, how the cache management is happening, cache move, mark it as dirty, drop it. So all of this, exactly how it is happening, we'll be able to see this, right? Other than this pager, for BTree also, although we have like a separate video altogether covering BTree and why do these databases usually use BTree, but this documentation is also very nice, that how it has n+1 pointers to sub pages. So the format detailing is mentioned. So how we just saw, right, that first we have a header string which shows SQLite format, and then there is page size, file format. By the way, can you see more light over here? Because it's morning. I have been recording entire night. So can you see some light more from this side? Because it is 6 a.m. right now. Cool. Anyway, I hope the entire effort of entire night, because I keep re-recording this and I keep trying to make the explanations as simple as possible, the entire effort of the entire night is going to be worth it if you can just hit that subscribe button and share. Just share with your friends or on LinkedIn or on Insta, wherever you are comfortable. It would mean just so much to me. Literally, it is morning. I can show it to you. I will put up an Insta status right now. It is morning. But cool, let's get back to it. So can you see file header, page header, cell pointer array? So this is how it looks like. OS level call. If you see the file over here is, we have the entire command with us. We are back to the exec command, but now what is the statement that is going to be done? Select all from the SQLite master. Because we have given primary key, it is internally creating an index. What is the SQL statement? Insert into SQLite master. The values are, this is the index. As soon as we saw primary key, here was the second part of execution. See, what is the statement? Update this set type table demo DB journal. There is demo DB journal. There is no journal. When I started my journey as a software engineer, I used to always think that only these super cool software engineers would be able to understand such complex code of databases. So yes, this is a dream come true for me also. As a teacher, this has always been in my to-do list. Because my ultimate goal as a software engineer, as a teacher, is to make such complex topics simple and to cover them in depth, right? So yes, welcome to another video in the free course of Databases in Depth by Educosys, where we not only cover databases in theory, but also debug the internal code. And yes, we are starting with SQLite, which is one of the most simplest but one of the most famous databases in the industry. This is the perfect database to get started with. We are going to be debugging the code. This is going to be super interesting. Thank you for showing up. Without wasting any time, let's get started. But before we get started, just one small thing. Although this is completely free for you, if you could just hit that subscribe button and if you could just share it with your friends or anyone who is looking to become a better software engineer, it would mean the world to me. It would mean so much. All my effort, all the effort behind this entire series would be completely worth it. So thank you so much for that. And now let's get started. Since we are going to be debugging the code, the first question that comes is, how are we going to compile and run such a huge project? Because if you see the source code, there are so many C files. It looks huge. How do we compile this? How do we run this? Because SQLite is supposed to be a very simple database. It is supposed to be embeddable. You are not required a different process for it. You are not supposed to have any extra configurations, nothing. It is supposed to be simple to use for small to medium level applications. So how is that going to happen? So if we open the official documentation of SQLite, and if you just go to this download button, you are going to get this page. So SQLite download page. And if we see the first zip file that we can download, it says SQLite amalgamation. See source code as an amalgamation. What does that mean? Let's see some more documentation. Here it says how to compile SQLite. So if we read about it, it says the use of the amalgamation is recommended for all the applications. Building SQLite directly from the individual source code files, that means from the GitHub source code that we just saw, is certainly possible, but it is not recommended. Then what is recommended? For some specialized applications, it might be necessary to modify the build process in ways that cannot be done using the pre-built amalgamation, which is fine, not from the website. But for those situations, it is fine. But other than that, use the amalgamation. What does that mean? So let's see. See, SQLite is available as a pre-packaged amalgamation source code file, which is SQLite 3.c. I know you might be a bit confused right now. Just stay with me for a bit. Amalgamation file is a single file of C code that implements the entire SQLite library. This is much easier to deal with. Everything is contained within a single code file. So it is easy to drop into source tree of a larger C or C++ program. What does this mean? Let's actually see the SQLite3.c file and let's try to understand. So I've opened the SQLite3.c file, and if we see over here, it is written begin file SQLite int.h. What does that mean? So if I just see begin file, do you remember we saw this in the starting of every single file when we were going through the code? And let's see what is actually happening. So if I just search for begin file, I've searched for begin file. Can you see there are 138 matches? And if I just keep going down, you can see vxworks.h, SQLite3.h, SQLite3r3.h, session.h, something.h, limit.h, hash.h, parse.h, os.h, ossetup.h, pager.h, btree.h, vdbe.h, opcodes.h, pcache.h, mutex.h, oscommon.h, ctime.c, global.c, status.c. So all the C and H files together, I think you are getting my point. And if we go to the top of the file, you can see what is written over here. So this file is an amalgamation of many separate C source files from SQLite version. By combining all the individual C code files into a single large file, the entire code can be compiled as a single translation unit. This allows many compilers to do optimizations that would not be possible if the files were compiled separately. Even performance improvements of 5% or more are commonly seen when SQLite is compiled as a single translation unit. So even I was trying to compile all the source code separately and doing all of that. But when I read the documentation, I was like, oh, this is just so cool and so easy to use. And that is why SQLite is famous, right? So this file is all you need to compile SQLite. To use SQLite in other programs, you need this file and the SQLite3.h, which I have right over here, SQLite3.h. And what it is saying is that this is what you need that defines the programming interface to the SQLite library. And there are more details mentioned that we can keep reading about it. And if we come back to our official documentation, you can see that a build of the command line interface requires 3 source files, SQLite3.c, SQLite3.h, and it is saying it requires one more, shell.c. So what this does is it contains the definition of main routine. So what I have done is I downloaded from here only, and when I downloaded there were 3 files. But what I have done is I have written my own main so that I can show you whatever commands I want to run. So let me show you that. So here you can see 3 files, SQLite3.c, SQLite3.h, and then there is one main file. This file I have written. So this is a simple main function, and inside this is what I am doing, and we are going to be debugging. So open the database, create table, insert, all of this, right? So I have commented the insert, update, delete for now. But what we are going to be debugging firstly is the create table, then insert, then select. We are going to be debugging like this the entire thing. As you can see, I have put breakpoints literally after every single statement in main. So it is going to be very clear. We are going to go one by one. Our major focus is going to be on the create table statement. Although it looks very simple, create table statement, there is a lot more that goes behind it, and we are going to see how much is there behind one single statement. For now, let's get started with a simple open database statement, and I'm going to build it and run it for now. So you can see I have a lot of breakpoints, and I'm going to show you the important functions that are going to be hit. And I'm going to be using the cursor as much as possible so that you know exactly what I am doing. Here, can you see right now there is inside DB. If you see, there is already VFS, VDBE. Do you remember these terms, VFS, VDBE a bit? Yeah. Let's see what exactly is happening. Let's go inside open. And if we use open, or if we use open version 2 internally, open database is called. So let's go inside this and let's see what's happening. So if we see the file name was demo.db, that is what is sent, that you have to open a database with this name, demo.db. And there are a lot of things that happens. You can see there is initialize and all of this, but let me show you the most important things. So for now, there is BTree open, correct? So you are opening the BTree sort of, and if I run it again, See, here comes the interesting part. So this is a OS level call. If you see the file over here is users, Kitibastani library, developer, Xcode, something SQLite test and build products debug. So let us see what is there in that folder right now. So let me just go to the command line quickly and let's see what is there inside this. So right now there is only SQLite.test and now let's do this. Let's run just this one line and let's see what happens. So we are inside robust open and if we go back and run it again, can you see demo.db? So that is where the exact file was created. Where? So if I show it to you again, this is where, because you're opening the file, right? So you are opening the file with, okay, if I just come like this, you will be able to see. This is where BTree open, pager open. So remember BTree to pager. So here you can actually see it happening. And this is the Unix open. So it got run. And everywhere, if you see in the Unix open also, what was the name that was given? Debug. And if you see the entire name over here, demo.db, demo.db. And this is the one that got created, correct? And we are inside this right now. So right now I just wanted to show that where it is being created. And if I just quickly run it, now we are going to be in the create table. And let's quickly just see what else is there. Right now our condition is there is demo.db and there is SQLite test. Before we run create table statement, let me tell you that internally there are a lot of commands that are going to be run in create table and it can be overwhelming when we directly debug. So let me give you some context and let me tell you exactly what is going to happen so that you have some idea and you know that why so many commands are being run. So let's do that. Before we move ahead, I would just like to take a minute over here to tell you that if you're preparing for interviews or if you're looking to become a better software engineer, I would love to be part of your learning journey and make it easier, faster, better and more fun. I teach live. Plus, you also get access to the recordings so you can learn at your own pace and you get a consistent teaching style because I teach all HLD, LLD, DSA, project-based courses where we cover industry-level projects like YouTube, WhatsApp, Zerodha. We cover MERN stack as well as DevOps and we also have C++. Plus, if you sign up for any of our courses, you get lifetime access to all the batches, the past, present, future, everything. You also get access to our mock interview platform. You can come practice anytime. We are going to guide you. We obviously have doubt support as well. We are putting our heart and soul into teaching. So if interested, at least check out the site. All the detailed curriculums, the testimonials, the answers to all the general FAQ, everything is present over here. Just check it out. Educosys.com is the site. Plus, if you still have any questions, feel free to reach out to us at support@educosys.com. We will also guide you about what is better for you. At least check out the testimonials for now.
The best thing that I like about Educosys is their courses are live.
Kirti herself, the way she teaches, the way the courses are structured are actually the best part.
Their live classes and the very helpful Discord community.
I feel very confident as compared to what I was before these courses as a software engineer.
My experience at Educosys have been really great.
I feel more confident as a software engineer after enrolling in Educosys.
But for now, let's get back to the video. This is the exact create statement that we are going to be running and debugging. So what is going to happen is first we are going to tokenize and understand and parse it. So first we are going to come across create token and then we are going to come across table. So we know we are supposed to create a table. Then we are going to see that when we come across this starting of the bracket, we know that we have our table name now. So what is the table name in our case? It is courses. So we know that we are supposed to create a table with the name courses. The first thing that we are supposed to do is make sure that whatever DB we have right now, there is no table or index with the same name. It is possible, right? So while our debugging, this is the first table that we are creating. But in reality, it is possible that there was another table or index that was created with the same name. And if that was the case, SQLite is supposed to throw you errors saying that there is already a table or index with the same name. So we are supposed to do this checking. Now, how do we do this checking? First thing that we have to do is we have to go through our database and see what are the present tables, what are the present indexes. They can also be triggers, views. So we have to first go through our database. So how do we do that? So for that, what we have is there is another special table that is created in SQLite, which is called SQLite master. So this is a special table that is created and it has the schema of all the tables, indexes, triggers, views that are created. I will actually show you The first statement that is supposed to be run is the select statement. So what we are going to do is we are going to run a select query on SQLite master, and we are going to see that what are the present tables and indexes, what are their schema, is there any table or index with the name courses already or not. Now, when is this SQLite master created? So because till now there is no table or no index that has been created for now, right? In our debugging, we just created the database, nothing else has been created. So in that case, there is yet another query that is going to be run. And the first query that is going to be run is going to be a create table query. So first we are going to create the table, and we are going to create what? We are going to create the SQLite master, and I will actually show this to you. And then we will run a select query to see all the tables and indexes that are there to read the schema. So this is the create table SQL command that we are going to be executing. So here we use SQLite 3 open. Now we are going to be running this command SQLite 3 exec. Here you can see we will be passing the query as well. So let's do that. Let's go inside this exec function. So if we come over here, we have passed the entire query, right? So initially, what is the first thing that we are supposed to do? We are supposed to tokenize it. So for doing that, firstly, there is going to be a prepare function that is going to be hit. So first we are going to take a log and we are going to prepare. So there is going to be BTree log. So we are going to take the mutex and all of that. And there's prepare. The main function that we are supposed to care about is this SQLite 3 run parser. Do you remember we saw this? So here we have the entire command with us. What we are going to be doing now is actually see the while loop, and we will see that okay, create table, it is tokenized, and can we see the tokens or not. So let's continue to the while loop. So see, while loop is going to start from here, and let's come inside this, and now you can see the entire SQL statement. Right now, what is the token type? So as soon as we get the token, right now the token type is 17. Why 17? So if we go inside this and see what was the token type for 17. So let's see, 17 is create. See, so what did we do in get token? You remember we actually saw this code. So if we go to get token, we had seen that we see one by one that what it is, right? So right now it is create. The next one that is supposed to come is space, right? And then after that table. So we are going to go one by one like this. So there is a while loop, and if we see this while loop is still where? So you can see the while loop is still here, right? And let me just continue and come back to the next iteration. So see, the next one is 184. So if we go inside this and see what is 184, so it is a space, right? So create space. The next one is supposed to be table. So if we go up and see what was the number for table. So for table it is 16. So the next one should be 16. So if I just continue again and I hit this breakpoint, so you can see it is 16 for now. And let's go to next and see what happens. So the last token is saved over here, and you can see the statement is also trimming off, right? Like because we have already taken care of create space, and now we are dealing with table. So one by one, see, here is where we are, n is the size of the token, right? And now that is how we are moving. This is like a simple while loop that we are just moving to the end of the next token, right? And just we moved over there. So now we are at space courses. So if I just do again, right now the token type is 16. And if I go to the next line, you can see that it is 184. Why again? Because it was space. So now we are going to be dealing with space. If I continue again, so now we are going to be starting with courses. Now what happens in courses? See, it is 59. What is 59? If we jump to the definition and see what is 59. See, 59 is ID. So there is some ID that is there, correct? Courses is an ID. Now let's see what happens. So where are we going to go? So there is also parser over here, right? So if you go inside this and if you want to see, this is how the parser looks like. Remember, we saw this entire thing that this is how the lemon parser looks like. So we can keep hitting this again and again, but why to see the parsing code? So I'm just moving ahead. You know exactly what is happening, right? If I move ahead now we are going to come across this bracket. So we know that we have now the name, and now we are supposed to see, we are supposed to read the schema. So let's see how that is going to happen. See what is the token type right now? It is 22. Let's see what is 22. So if we go back over here and we see what is 22, see it is LP. So I think it stands for parenthesis. And if we go inside now, see, so when the parsing happened, I had put a breakpoint over here. Now it is saying that you have to start the table. So this is where we are going to start the table. See, all the parse structure is there. So inside this you can see VDBE and all of this is null right now. Let's go inside this and let's see what is going to happen. So now we know that we are supposed to start creating a table, right? Now comes the interesting part. So now we have tokenized till create table, courses and then bracket. So we know that we are supposed to start a new table. So what we are going to do is we are going to initialize. So can you see over here, we are going to try initializing something. So firstly, okay, let's move ahead for now. So you can see that the name is there. So, okay, let me just show you the name. Give me one sec. Yep, can you see it over here? So this is the token. So here the entire thing is passed over here. So what is the remaining token has been passed. So let's go ahead. We are doing some auth checking and let's move ahead for now. Now can you see we are going to read the schema. This is exactly what I was talking about. Make sure the new table name does not collide with an existing index or table name in the same DB. Issue an error message if it does. So here you can see we can issue an error message that the view already exists or the table already exists. Okay, there's already an index name this. So if there's an index name this, we can also say that. Okay, so we have to first of all read the schema. So let's go inside this and let's see that how do we read the schema. Okay, and if we go inside, here is where we are going to be reading the schema. This routine is a no op if the DB schema is already initialized. Because the schema is not initialized yet, this is the first statement that we are going to be running. So that is why we are going to run the initialize. And let's go inside this. And because this is the first time, we are going to be going inside the init function. And you can see we are inside initialize. Initialize all DB files. The main DB file, the file used to store temporary tables, and an additional DB files created using attached statements. Now let's see exactly what is happening. Next very important function that we should be looking at is init1. And let's go inside this and let's see what is happening. So if I go inside this, you can see that some transaction, okay, right now I think I can continue. And let me just continue for now. And see, I am inside init1 and you can see there are some things that have been done. And here you can see we are forming a new statement saying create table X, type text, name text, table name, root page and SQL. This is the schema table that we are creating. Okay, this is the schema table and the name we are going to give it SQLite master. So in this file actually if I just search for SQLite_master, so you can see there is a legacy schema table that is going to be created. Similarly, there is a temp master that is going to be created, legacy temp schema table. So what we are creating right now is the legacy schema table. So if I do next, here you can see this statement is saved in this argument. And what we are going to do is in this callback, we are actually going to execute this new command. So this is a new command altogether. So again, whatever we have seen so far, so prepare, lock and prepare, run parser, all of this is going to happen again for this new command. So this is a new SQL command altogether. So within a create table command that we are running, internally there are a lot of commands that are going to be run. So here you can see we are constructing the in-memory representation schema tables. So SQLite schema or SQLite temp schema by invoking the parser directly. So now this entire table is going to be created. And interestingly, the schema of this schema table is also very important because you will see that within this table, we are going to store schema of all the tables, indexes, views and triggers. So when you see type, type is going to signify. So here can you see the type? So what we are going to pass is a table because we are creating a table right now. So in the type, you are going to say whether it is a table, it is an index, it is a trigger or a view. Then this is where you're going to store your table name. This is the name of the object and this is the root page number. So you remember every B tree, so there is a root page. So this is the page number of the root page of the B tree, right? And this is where you're going to store the entire SQL statement that created this particular table or index. And you will see later also when we are going to compare the schemas, you will actually see that the entire SQL statement that you were running. So in our main that we are saying, no, create a table, this is actually going to be stored as it is within this schema table, because the entire SQL command that was run to create this particular table or index or trigger or view, that entire SQL command is going to be stored, so that you can check the schema of that also. So whenever you're going to insert, it is going to validate that, see, this was the SQL command that created this particular table. Now you are saying to insert, is the schema matching or not? Because how will it do the validation that, okay, you are not sending any particular field that is supposed to be not null or primary or something like that. So this table is going to give you the entire schema. So that is why this is a very, very important table. So see, this is where we are saying that this is going to be a statement. So if I continue now, see, now we are in callback, and if we go ahead, so if I just go ahead and continue, actually, you will see that I am going to prepare. And what are we passing? The fourth argument. What was the fourth argument? The entire SQL statement that we made there and we passed, right? So this is a huge code, but I am showing you the most important thing. So we are in the init callback right now, and we are passing that fourth argument. And this is where the statement is going to be there. And see, right now we are back to prepare. So where did we start from? So from our main, we went to exec to prepare to run parser. Now again, parser will be run. But if you see now, what is the statement? That it is the new statement. It is not the statement that we gave in main. It is the statement to create the SQLite master table. So if you see, this is the type, table name, root page, SQL text. Again, if I continue, now we are going to again parse this. Again, we can see the while loop. See, again, you can see the tokenization. Here you can see right now it is 17 create. And if I do again, it is going to be space, so 184. If I do again, now it is going to be 16, so 17, 184, 16, just how we saw earlier. And if I do again, so it is going to be of the type 184, again space. And if I come now, it is going to be 59, which was ID. And if I continue again, now let's see what is going to happen. Again, we are back to start table. But now what table are we starting? The SQLite master, and not the table courses that we were supposed to create. So this is interesting, right? And if we go inside this, see, if we actually see the names right now. So here, can you see this entire, see, type, text, this, and X is going to be sent separately. So if we see, you will actually see the X name as well. Let me just show it to you. So here, can you see right now? No. See, now when we read the schema, okay, so I pressed continue, but what you saw was that right now init was not hit, because this is not true now. We are not going to get inside this because we have already set the state and we are creating what? SQLite master. So if I move ahead now we have said it, okay, we are going to start creating the table, and this is what we are going to be passing. So now we are going to tokenize the rest of the SQL statement. So we are inside the while loop. So there was type, which was of 184, then there's going to be space, then 59, right? So text, comma, so if we see 59 again, and if we do name, then can you see this moving? So text, then text is gone now, comma. So we are just going through the rest of the statement. So we can debug it like this. So root page, space, int, comma, SQL, and then text. So right now we are just tokenizing and parsing the rest of the entire statement. And what is going to be the important moment now when we come across the bracket? That means that now we have all the things. Now we are ready to create the table, right? So if I do continue now you can see we are in the end table. What does this mean? This means this routine is called to report the final this that terminates the create table statement. So now we are saying ki now we have tokenized past the rest of the statement. Now we are at the end of the create table statement. Which create table are we doing? Create table of the SQLite master. So we are at the end of that. Let's now see what happens inside this. So when we are at the end, so here we are just checking and we are going to set some flags and everything and initialize the entire table. So schema to index, and I'm just going to continue for now. And here we are saying parser finalize because whatever engine was there. Now we are done with the creation of SQLite master, and I'm going to continue again. And now we are in SQLite 3 finalize. So do you remember while executing any SQLite command, so we go through SQLite exec and then there is finalize. So this is finalize for what statement? So the statement was the creation of that. And here you remember, so whatever statement is there, that becomes the VDBE, the engine. And let's see. So right now there is no statement. So we are just going to go ahead and we are going to see the finalize in the next statement. So that's fine. And let's just go back. Let's just move ahead. So now we have created the table. We have created which table? We have created the SQLite master table. So this init callback is now done. So a quick recap from the create table of courses that we were creating. We went to read schema and then we saw that okay, nothing has been created till now. So we have to create the schema table. So this is where we created the schema table. We are done with initializing the schema table. So now what is the next thing that we are going to do? If we move ahead, okay, if we move ahead, so you can see there is BTree transaction that we are starting. Now that we are clear with that much, you should know that we are still in our init, okay. So I'm just going to continue and go to the next important thing. So right now, just know that this is the huge function where we actually created the table. So created the SQLite master table, okay. So we are still inside init1. So if I just go to next, we are still inside that, but now we are going to run yet another SQL command, which is select all from. What is that we are selecting all from? From SQLite master. So the very first table or index which will be created, at that time we will be creating the table. But if that is done, see, the create table statement is not going to happen again and again. Because this was the first table that was created, that is why this was called. So if you see init busy is the variable that they are setting to see that okay, this is the first time that we have to create. Now that it is created, what we are going to do is we are going to select all from it and we are going to see the schema now. So now we are going to see the schema. So now next time also when you create a table in this database, every time you create a table or index or anything, this will be run. So if we come inside this, we are going to select all from this and now we are going to execute a select query. So within a create query, we have now run a create query and now we are running the select query. And if I just move ahead and if I just do continue, so we are back to the exec command, but now what is the statement that is going to be run? Select all from the SQLite master. And from where did we call this? So we were just over here right now, right? SQLite all from the master table. We just saw this. So we are just inside this right now and there's also an init callback inside this, okay? So if I just continue, this is the statement that is going to be run. Again, we are going to prepare. So if I do continue, again, we are in lock and prepare. And again, we are in prepare and now we are again going to be where? Run parser. But now what is the statement that is going to be passed? Select all from. So if I again do continue, again if I tokenize this, what is the first token that is going to be there? 138. Let's see what is 138. So if I jump to definition and see what is 138. So you can see 138 is select. So it is what? Select all from. So the next one is supposed to be asterisk, which is all. So if I just do continue, the next is 108. So if we again see what is 108. So let's see what is 108. It is star. See, so select all and the next one is supposed to be from. So if I just search from over here, okay, it will start searching in the entire file. Let's just go ahead and let's see what is the next one. So what is the token type right now? It is 108. If I run again, it is 142. Again, let's jump to the definition and see what is 142. It is from. See, so select all from. And if I do continue again, here you can see 141. Again, what is 141? So if we go to the definition 141, it is dot. Okay, so this dot it is trying to see. Then we are going to come across SQLite master. And the next is 59. 59 was what? I think ID, correct? So 59 is ID because SQLite master is ID. Next should be space, which I think was 184 or something. Let's see. Yes, space is 184. So if we run it, the next is space, which is 184. Now then it will be order, then again 184, then by. So if we do continue again, it is 145. So 145 should be order. If we see 145 is order, then it should be 184 again. Yes. And if we do continue again, it should be by. So if it is 34, let's see. 34 is by. And see, right now I am showing you only the tokenization part, but within this while loop, every single time we are going to the parser also. So if I just put like a debugger inside this, if I just do this, you can see that within every while statement we are coming inside this only, and within this there are if and else. So now you should be able to understand it how tokenization and parsing is happening properly, right? So if we see over here, there is a while one for parsing also. So if I just continue, we'll be back over here, and it is again space. And if I continue again, now there will be row ID, and again we are going to be parsing. And if I continue now, let's move ahead, and now we are in select, right? Where did we go from select? So in our reduce, just how we came to start table, right? So if you remember over here only, there would have been a start table somewhere, and that is where all the if else are there. So there is drop table, create view, drop table, and select, and there would have been a breakpoint over here somewhere for start table that we just hit the last time. Right now we are in, so yeah, you can see over here, correct? So you can see add not null, add primary key, create index. So all of these will be hit. So right now we are in select, and let's move ahead. So what is going to happen is, now we are selecting the information. We are getting the information from where? We are getting the info from SQLite master. So that is the table that we are reading. Let's quickly move ahead and see what is going to happen. So this is select expander, and this is how selection is going to happen. I think we can just continue. So see, we are reading the schema again. Right now it should not go into the if statement. So because initialization has been done, right? See, it did not go into the if statement. It is going to go inside the if statement only the first time. Only the first time we are creating any table or index or trigger or view. Only the first time it is going to go inside that, after that not. Okay, and right now we are going to go to find table. We are going to find a table with the name SQLite master. So you can actually go inside this, and when we do find table also, it is again going to check in the DB only, right? So it is going to compare, is there anything with the name SQLite master, and then it is going to compare one by one. See SQLite underscore, and it is checking. Are we finding the schema table or the temp schema table? So we are finding the schema table, right? So if we go actually ahead, so we are going to locate the table now. I'm going to just continue from over here, and we are in parser finalize, and let's run it. And now we are going to execute the statement. Which statement are we executing? We are executing the statement select all. So what did we do till now? We just prepared the statement, all the initialization happened. Where does the actual execution happen? In the step, right? So if we go inside this, see, you can see this is where the execution is going to happen. So now we have the prepared statement. So now we are moving from the front end to the back end of SQLite, correct? So this is the top level implementation of SQLite 3-step. Call SQLite 3-step to do most of the work. So this is where the actual work is going to start. If you can see, the prepared statement is now typecasted to VDBE, right? VDBE is our first component in the backend of SQLite. So we are now in VDBE. We are taking mutex lock, and let's move ahead. So do you remember what exactly happens in VM? VM is nothing but a huge switch statement, and there are opcodes within, right? So this is the opcodes, and there are operands and all. We will not be discussing up to that level, but you can see the switch statement. So can you see the switch statement being executed one by one? So if I just move ahead, and if I just show you, see, this is the switch. So this is where we are going through every opcode one by one. What follows is a massive switch statement. So do you remember in VM, there is only a huge switch statement, right? That is why understanding the basics is very, very important. So here there are some opcodes and there is a switch statement in the VM. So let's continue for now. And I just wanted to show you the switch statement once, and I'm going to remove the debugger from there and just going to continue. So this is VDBE halt. So now VDBE part is going to be finished. Let's move ahead. And you can see BTree commit phase 1. So a quick recap of exactly what is happening. So we are executing the select all statement from SQLite master. So we were in the exec statement, right? From there we went to the step. This is where the actual execution happens. And now we have the prepared statement. So in the step is where we are going to be typecasting the statement, the prepared statement to the VDBE pointer. So now we have the VDBE pointer, and then we saw there was a huge switch case that was executed for the opcodes. Now from after the VDBE component, what is the next component that is hit? It is the BTree one. Now in BTree there are two phases, phase 1 and phase 2. And BTree component will be using which component? The pager component. So within BTree phase 1 you can see there is pager commit phase 1 call, and similarly within BTree phase 2 we will be able to see pager phase 2 call. So right now there is a select statement, right? We will see the commit phase 1 and phase 2 execution later. For now I am moving ahead from phase 1, and now we are going to phase 2 for the BTree. And if I go ahead in the BTree phase 2, see if I just go ahead and I am outside, and now we will be doing the commit. And if I just continue for now, and we are going outside the VDBE part, and I think we can just return. If I just go out, I go out. So we are coming out of this step, right? So we are coming out of this step. If I just continue, VDBE finalize. So we are doing what? We are doing the cleanup and delete the VDBE, okay? And DB free. And right now we were executing what? Select all statement. So remember that. Again phase 1, phase 2, init 1. And now let's move ahead and see where are we. So the create table part is going to get executed again. Let's move ahead, call back, prepare, again prepare, parser. What is the statement right now? It is create table. I know the question right now is, how did we get into create table all over again with the type text name? So this looks like schema of SQLite master, right? How are we creating SQLite master again? So no, we are not creating SQLite master. We are creating a temp master. I know it can be confusing. Just stay with me, stay patient. How tokenizer part is now completely clear, right? Slowly it will become clear. Let me do a quick recap for you to completely understand what is happening. We started from create table courses. Then we did a create table of SQLite master. Then we did select all from SQLite master. That happened. Then we were still in init, and still create table is called again, right? Create table is called again. But now what is the X value that is passed? So now let's see that, right? So if you go ahead and come to the parser, and if I just go right now, so the value of X should be what? So if I move ahead and I just do this, and let us just actually go to create table, and I'm removing the breakpoint from over here, and I'm just going to go directly to the start table now. See, start table. What is the name of the table that has come? Let's see. So let's move ahead. Let's move ahead. What is the name? So it is a schema table is what we know. And let's move ahead. Let's move ahead. Just stay patient with me. Stay with me. Okay, we are checking. Is it already there? We are doing some auth check. We are moving ahead. And now we are reading the schema again. Okay, I know it can be confusing. Stay with me. Stay with me. Come on. Read schema, find table, and let's see what is the name. SQLite temp master. So you remember when we saw SQLite master, the legacy table. So if we just search SQLite _ master, if I just search that, so there was the legacy schema table and there is legacy temp schema table. Now when is this created? Why is it needed? So this is to store schema of the temporary objects. So whenever we are creating a new schema, no, this schema table is created, the temp schema table is created. So this temp schema table is responsible for temporarily holding the schema information, because we are creating a new schema in SQLite master, right? We are creating a new entry altogether. because we are doing that, temporarily we are going to store it in SQLite temp master, and that is why we first have to create the SQLite temp master. So the first create statement is actually going to be a lot more complex, the first create table statement of the entire DB. But once all of this happens, you don't have to keep creating SQLite master over and over again, right? Because it has already been created. So after that, things become much more simpler. But because this is the first time, it is also interesting because you will be able to understand, right? So now what we are creating the SQLite temp master. So if I just run right now, and now we are back to type text this. Now what is the remaining? This we are creating again the SQLite temp master. So I am going to run, see text, comma, name, just notice over here, space, text, comma, just keep noticing this, table name. So the schema is same only, it is just for temporary objects. So the schema of SQLite master and SQLite temp master is same only, that is why all of this is same, correct? So text, comma, root page, space, int, comma, SQL, space, text. Now as soon as we come across this, what should happen? End of the creation. So end table. This is where we are at the end of the create table statement, right? So what are we ending? Creation of table of SQLite temp master. So I will run now, parser finalize, I will move ahead, and SQLite 3 finalize. We are finally done with creating the temp master. And let's move ahead. Now we are in which one? Now finally we are done with creation, selection of SQLite master and SQLite temp master. Now we are going to get started with the rest of our courses wala table. So if you go back to this, if you have forgotten, so this was the command that we were running. Till now we have run only this create table courses. Now ID, int, primary key, not null, title. So there are three things. One is the ID, title, and then duration in weeks. So if we go back over here, so if I just go to the next statement, here you can see ID, then title, duration, right? So right now we are in this bracket. So 59. So if I go inside this and see what is at 59, see 59 is the ID. So we are at ID, right? ID. Let's just run this now, okay? Now when we come across primary key, what is going to happen? Now we have to register a primary key, right? Because when we say create table, it has to register somewhere that, okay, this is a primary key. So that also should happen internally in SQLite, right? So currently the token is 184, and if I just go to the next statement and I move ahead, see, as soon as I come across the parser, so this was the space, and as soon as I move ahead, can you see add primary key? So we came over here. See, we are in add primary key. How did we come here? From parser, again we reduced to add primary key. So as soon as we saw, okay, primary key space, then we saw, oh, we have to register a primary key. So inside primary key, if we come, what are we supposed to do? We are supposed to create a new index, right? This is exactly what is supposed to happen internally in SQLite, right? Because we have given primary key, it is internally creating an index. So let's go inside this and let's see how is the index created. So if I go inside this, see, now we are going to create index. Let's move ahead and see. Let's just go ahead. So again we are reading the schema. Again we are in init. Again we are going to see. Okay, just give it one sec. So we are in init right now. Init is done. See, schema to index. So if we go inside this, if the same DB is attached more than once, the first attached DB is returned. Okay, so we are going to continue now. Okay, so now comes the next important part. Within create index, what is the next thing we are supposed to do? We are supposed to insert this index. Where is all this information of all the tables, indexes, triggers, views? In our schema table. So in our schema table, we have to say there is a new index. So inside our create table of courses, because we had given primary key, it is going to create an index. And what is going to happen when we create an index? We are going to insert that index into our schema table. What is the schema table? SQLite _master. And what exactly are we going to store inside this? So if I just do run Again from nested parse, what do you think is going to be called? If I do just continue, see run parser. What is the SQL statement? Insert into SQLite master. The values are, this is the index. What is the name? SQLite underscore auto index underscore courses underscore 1. So for the courses table, it is creating an auto index and the name is underscore 1. See, if we remember the scheme of SQLite master, how did it look like? So first was type. So what was the type initially? It was table. Right now it is index, because what are we inserting? The index, right? And this is the name of the index. This is the table name, the courses, right? And this is the SQL command that is going to be run. And this is what? It is the root page number. So that is 4. So let's move ahead for now. And we are going to parse. So let's again go inside the while loop. What is the token type? It is 127. And let's see what does 127 stand for. So 127 is insert, right? Because this is the first time we are seeing insert statement. We have already seen create. We created the SQLite master. We created the SQLite temp master. We also did a select all from SQLite master. Now we are doing insert index, right? And now we are running the insert statement. So I am going to run now. See, insert space and then into. So 151, if we see, 151 is into, correct? And if I do again, so insert into, then it will be main dot SQLite master space values and then this. And I am just continuing and moving ahead. And as soon as the insert statement finishes, what just happens? So in here you can see SQLite 3 insert. From here we came to insert. Just how we went to select, right? Now we are in insert. So here you can see there's a huge insert statement. So if we come inside this, now what we are going to do, if this is not a view, open the table and all the indices. So this is where we are going to open the table and indices. If I go inside this, you can see what all things are happening. Schema to index, and I'm going to continue for now. Again we are back and we are finishing the insert statement. Parser finalize, moving ahead. Primary key is now done. So back to our original statement, primary key is done. Now we are in not null. Okay, let's continue. So you can see not is done and then space. Now null is being executed. And as soon as I do this, you can see not null wala parsing is going to happen. And if we go inside this, it is going to mark it as not null, right? Because in our schema, it is supposed to update that it cannot be null. That is why the next time when there is any insert into the courses table, it will be able to check the schema and say, oh, this is not supposed to be null. So we're supposed to update the schema now, right? So I'm going to continue. And you can see text space not space null. Again not null will be hit. Then duration int. Again not null will be hit. See, not null is hit. So if you go inside, you can see it adds the not null wala part. Okay, so it just updates the column that it is supposed to be like this. Now we are finally finishing what? The create table courses. Finally we are going to do this, and we are finally in the end table of create, right? And if we just continue for now. Okay, I know you're overwhelmed. Let's do a quick revision of exactly what has been happening till now. So this was our original statement. We went to create, we went to table, then we went to courses, and as soon as we came over here, there was a lot that started happening. So let's quickly write it down what all things happened. So when we came over here, we did first, because this is the first time we are creating any table or index or anything. So that is why the first thing that happened was create table what? The SQLite master, right? The SQLite master. Sorry for the handwriting. Now within SQLite master, what was the schema? So how does the schema look like? There is type, which was like index or table like that. Then there was name. Then there was the table name. And after that there was root page number. And then there was the SQL text, correct? So this was the schema of the SQLite master. Now after we created the table, what did we do? We did select all from the SQLite master. Why did we run this command? Because we had to check for conflicts. So check conflicts and gather the current state. So current schema state. So that is what we get from the select statement. So first we did the create statement, then we did the select all statement. After this, what happened was we did one more create table. Because why? Because we are creating a new schema itself. So that is why we are creating a temporary object, and for that we need the temp table. So now we did create table. It was for the SQLite temp master, and the schema of SQLite temp master is exactly same as this: type, name, table name, root page and SQL. So the schema is exactly the same, just that this table is for temporary objects and this table is for the main objects. Now one more important thing to remember, that in the select statement you actually saw that within step we did the VDBE calls. So there was VDBE exec and VDBE halt, and after that we did the VDBE commit. After that we did the phase 1, phase 2, right? And in phase 1, phase 2 we saw that there was BTree and then there was pager. So you saw the flow that in select what was happening, that first we prepared the statement which is like front end of the SQLite, and then once we had the VDBE pointer, we did the opcode wala switch statement, then VDBE commit, and then it used the BTree layer used the pager layer, and then the OS layer gets called. So all of this happened till we were over here. Okay, so this was like first part. So all of these were like the first part ka execution. Then we executed all of these tokens, and then we saw primary key. Oh, as soon as we saw primary key, here was the second part of execution. Because we have seen primary key now, what needs to be done? We need to insert a new index. So that is why what was the call that was made? That insert into, so insert into the SQLite master. And what were the values? So I am literally just seeing, okay. So the values were index because that is the type, right? So that was the type. So here you can see the type. So the index was the type. Then the name was SQLite underscore auto index underscore courses underscore 1. So that was the index name. Then there was table name which was courses. Then there was root page. If you saw, we saw something like this, right? That was the one. And then there was SQL statement which was null. So we did the insert into statement. So this happened. So this insert into statement happened because of this primary key. And once this happened, then there was not null and all of this. And then once we ended, once this happened, now all of this is done. Now we have reached the end table. And from here, now we are seeing yet another command, which is the update command. Coming back to our update statement, now why is this happening? A slot for the record has already been allocated in the schema table. We just need to update that slot with all the information we have collected. Like for example, the SQL statement, the root page, all of this information we have not set properly, right? So now we are updating the schema table. So this again legacy schema table itself, which is the SQLite master. Here we are saying, see, this was the SQL statement which created. So let's actually, if we just go ahead with this. So from here again nested parse, and from here what should be called according to you? Run parser. See, what is the statement? Update this set type table. Name was the courses, table name was the courses, root page is 2, and the entire SQL command. So if you see over here, you can actually see the entire SQL command, right? So if I again do this, this is our SQL command. See, create table, courses ID, primary key, not. So whatever SQL command we use to create this table, that entire SQL command is going to be saved in SQLite master. So now if I just go ahead, so again tokenization, parsing, all of that is going to happen. See, now it is 129. So if we go to again 129, let's go to 129, see update. So within one create table, you saw create, you saw insert, you saw select, and now we are also saying update. So if I just move ahead, update, then main.SQLite set type equal to table space name equal to courses, comma, table name equal to courses, comma, root page equal to then SQL equal to the entire SQL statement. This should be one text. So if I just do this, see that was one text, space where, space row ID, again the row ID is there. And now we are done with what? We are done with the execution of update. So if I just move ahead, see parser finalize. If I go ahead, VDBE set SQL. We are setting the SQL over here, and let's move ahead. And after that, so we are in prepare. If I just move ahead for now, see where are we right now? We are back to the exec statement of which one? Our initial SQL statement. So now we are done with the preparing of our first statement that we said, the create table statement. See it properly, create table courses, whatever. So now we are done with preparing the entire thing. Now we are going to execute this. Now we are going to go to step and we are going to execute. See, we go inside this. If I go ahead, now we are in step. See, statement is now completely prepared. Now VDB is ready. Now this VDB, again from where? VDB to BTree to pager. Now phase 1, phase 2 should happen. If I move ahead, see step, just move ahead, VDB exec. So it is going to take care of our opcodes and all. And I'm going to go ahead. See BTree begin transaction. So from VDB to BTree, correct? And if you can read about this, about BTree, what is happening, we are starting a new transaction because we are creating the table, right? So I'm just moving ahead for now. New database, pager write. See, now from BTree to page. So now we are actually writing in the page. So let's see what is going to happen. Let's go ahead, pager write. And here, see, now I have opened a journal. Now something interesting. Okay, let's go to our terminal and see. If I do ls right now, there is demo.db and SQLite test. What was there initially? Okay, let's run now. Let's go ahead. See VFS, you remember VFS layer, we have hit that. And if I just go ahead, see, journal open. Okay, again, let's check what is there. Only two things. Let's come back and let's run again. And now open file. What file is being opened? Debug something something. So here you can see demo db journal. Journal is what? It is going to be created as temporary. It should be deleted later also. We are creating it and it should be deleted once the transaction is over. So right now again I am showing you. See, there are only two things. If I just move ahead, now we have opened, and if I do ls now, see there is demo db journal. And this should be deleted once we are done with this entire transaction. So once I come back, see, I go ahead and I'm going to continue, and I'm going to continue. So open is done. Okay. And here we are going to make the page as dirty. Remember what is a dirty page? When the page is different from whatever is there on the DB. So we are marking it as dirty. So you can go over here. Make sure the page is marked as dirty. If it isn't dirty already, make it so. Okay, so that is what is happening over here. We are managing the dirty list. We go ahead. See, this is the linked list wala code. This is where we are managing the entire thing. Magic header. So do you remember on the page on the top there was given that what is there in the header and all. So there is magic header also, if you remember. And if I just go ahead. So this is how we are setting the page. So here you can see every page we are making the changes. We are setting the, you remember in the offset it was mentioned, see SQLite format 3. Do you remember at the top of the file there is SQLite format 3. So this was also mentioned somewhere in the documentation. Let me show it to you. See, this is how the format of the file header looks like. Header string is SQLite format 3. This is what we just saw. After this, there should be page size and bytes, file format write version, file format read version. So if I go next, see, if we just see the data, there is SQLite 3 right now, then there is mem page and all of that. If we just go ahead, 0 page. So we are at the 0 page right now. This is how we are setting all of those information. See, cell offset, data offset, overflow, init. So we are setting, is the page overflow page or is it a BTree page? What is it? So all of that is also happening. So we are in transaction right now. Let's move ahead. Schema version. BTree begin transaction. Opcode. So we are in VDBE right now. Let's just move ahead. Pager write. So I'm removing the breakpoint from here because we're going to be making the changes in multiple pages. Now we are in BTree create table. See, create a new BTree table right into this. So this is where we are finally creating the table. So there is a new BTree for every table, right? So this is where we are creating that. And see, allocate BTree pager write. So this is where all of this is happening. So pcache dirty, again make dirty, manage list, 0 page. I am just removing the breakpoint now. See, now in the BTree we are going to insert. So we were first created the BTree, now we are inserting in the BTree. Create table, pager write, make dirty. Okay, so we are back to preparing yet another statement, which is select all from SQLite master, where all of this, right? So what we are doing right now is we are in VDBE exec. So what this does is, this is like a final verification that we have created the entire table properly. So it is going to go into the legacy table, which is again SQLite master. It is going to retrieve everything and it is going to check properly that everything has been done properly. So it is going to check that there was no corruption, there was nothing that happened. See, there is one error message for corruption also, right? So here we are just making sure everything's working fine. The creation of table was successful. So we are going to select everything. It should not be a trigger, but everything else. And we are going to continue. So here again prepare, again we are in parser, again we are going to tokenize. See, select all from, so select all from main SQLite master where table name equal to courses and type is not equal to trigger order by row ID, right? So this is where we are doing the select. So again select was called. How did this happen? From our parsing we went to select. So now we are going to select from the SQLite master. This is we are finalizing this particular execution. So now that we are done with that, we can move ahead. Now we are finally executing the statement. If we go ahead to this, again VDBE exec, so there will be opcodes. I'm just moving ahead. By the way, we should check, if we do ls, you can see that the journal file is still there. Let's move ahead. Continue. So exec, callback init, callback, init, callback, prepare. Now what statement is being prepared? Create table courses, the same one. Why? Because we are reading from the schema. Now let's again do this. Run parser. Again create table. Again primary key, not null, create index, all of that is going to happen again. Because now we are actually reading from the schema table and executing the entire SQL all over again. We are just making sure that that statement is running fine. And end table, so now we are done with that. SQLite 3 finalized, step. Now we are going to finally execute it. So we are in the step part, and from here where do we go? VDBE exec. From here where should we go? BTree, from BTree to pager, right? Let's just move ahead for now. If I just remove this. Init callback, step, VDBE exec, VDBE halt, VDBE finalize, DB free, VDBE halt, commit, see BTree commit phase 1. If I go inside this, let's move ahead. See, pager commit phase 1, and now we are finally doing pager commit phase 1. Okay, so we are inside this. See, we are writing the super journal and we can go ahead. See, this is where we are going to be dealing with this file. And let's move ahead. We are finally writing to the page. Finally writing to all the concerned pages. Phase 1 is complete. BTree leave. Now we will go to phase 2. It is checking for all the BTrees, right? Done. Now we'll go to phase 2. Now in phase 2 what happens? Phase 2 is when the journal gets deleted. So in phase 1, we just update all the information. So if we see journal is still there, in phase 2 is when we delete the journal, correct? So we go inside this. Let's go over here. We are ending the transaction as content, end transaction, BTree leave. Let's go ahead. VDBE commit will happen. And let's actually check now. See, there is no journal because phase 2 got executed. So what do? We delete the journal in phase 2, right? So our understanding is clear. Congratulations. This is a great part to understand, right? Now we are coming out of VDBE commit, coming out of VDBE halt, VDBE exec. So now we are finally done with executing our statement. I think we'll be out now. VDBE finalize, VDBE delete, done. Freeing the DB, coming out. Finally, we are finishing with create table statement and we are done. Give yourself a huge pat on the back for staying till here and understanding the entire execution of create table statement. It must be really interesting to see that within one statement, there are so many things that are happening, right? The indexes are being created, the schemas are being saved internally, and all of that happens. Now, although we have already seen insert, select, update, all of that happening, let's quickly see one insertion into the courses as well. So let's go ahead with that. And let's go ahead and inside the exec. So once we go inside the exec, you can see there's the SQL statement. Obviously, the first thing that's going to happen is lock and prepare, then run parser. So now you must be able to understand this properly, right? So now the insertion is going to happen. So tokenization, parsing, so insert into courses, ID, title. So once all of this happens, once we are into the insertion part. So right now we are going through the values. Let's move ahead. So we are into the insert. Where did we come from? From the reduce part. So from the parser we came to insert. Now we are going to move ahead and let's move ahead with insertion. So this is just to show you one final flow. Let's see, this is how we go ahead from here to VDBE to BTree. So I just wanted to see that once. So open the table and all the indices. We go ahead, parser finalize, VDBE, right, set SQL. So now we are going to execute this statement. When we go inside the execution, we now have the VDBE part, right? Now we have prepared this statement and all of that has happened. So the front end is done. Now we are in the back end part. So now we get started with VDBE. We move ahead. So VDBE part, VDBE exec. So now we have the opcodes. There will be switch statement. Now BTree part, right? So BTree begin transaction. So here you can see BTree is there. Now BTree has the pages, correct? So if we go ahead, you will be able to see. So VDBE accesses the component BTree. BTree uses pager. So now the component part should be completely clear, right? So see cache table lock. Then we move ahead. See now we have a mem page. Schema version, so we are getting from the page. So schema version is what? 3. We already saw that, right? We can just go ahead right now. See pager right. So if we go ahead for now, open journal. If we come back to the command line and see, so right now there are 2 things only. See here you can see that pager component is using which component? VFS component. So that part also you are able to see. This function is called at the start of the every write transaction. So this is the one where we open the journal. So if I just move ahead, journal open, and as soon as I go ahead with this, now if I go back and show you, see now there is journal. So for every write transaction this opens. Let's move ahead again. So we are making that too dirty. So if we go back, you can see we came from pager add page to rollback journal. So now we have added the page to rollback journal as well. And if we go ahead, we are going to write. BTree insert is happening. Pager write is happening. We are marking it as dirty. We are adding it to journal. All of it is happening properly, right? And so now the understanding is clear. VDBE commit. From VDBE commit, where do we come? BTree commit phase 1. As soon as we go inside this, we will go to pager phase 1. Let's go inside that. See, pager phase 1. As soon as we go inside the pager phase 1, what all things are supposed to happen? See, pager flush on commit, right? Pager write, pager add page to rollback journal, OS write, so I can move ahead. Now we are going to be in phase 2. If we see right now it is there, after phase 2 is completed, the journal should not be there. So let's come over here, see pager phase 2. As soon as I go inside this, we are ending the transaction, right? As soon as we commit and end the transaction and we come out, see BTree leave as content, we are just leaving from everywhere. And as soon as we come out of here, see journal is gone. So in phase 2, journal is deleted. VDBE finalize, DB free. We are done with the insert statement. We are finally closing our DB and we are done with one entire flow. So we first open the DB, we created the table, we inserted it into the table. Select statement we have already seen multiple times from the SQLite master. It's same as that. You can try it out yourself. I would now like to really thank you for staying till the end of the video. I hope you enjoyed this. This is very interesting and very different kind of video. If you have stayed till here, you're genuinely interested in software engineering and not just doing interview prep or just doing it for the sake of work. You will look really interested because only then you would go through the entire video, and I'm really proud of you for that. Thank you so much for letting me being part of your learning journey. If you like the video, if you are finding the series helpful, please do let me know in the comments. If you have any feedback also, if you would like me to cover any more parts. Just in SQLite itself, obviously I could go into a lot of detailing. So here's the plan. We started from SQLite, which is one of the most simplest databases. And after this, we'll be covering MongoDB, Postgres, Cassandra, Redis, and a lot more. So once we cover all the databases, at least the basic flows and the debugging, then we can also start going through minute details of each of these databases, and I would love to do that. But I can do that only if I know that you all are enjoying the series, only if it reaches more people, because you have no idea the amount of effort it takes behind this. You first debug the entire thing, you analyze the entire thing, you read through the documentation, then you think how to make it simpler, and then you make sense of why are so many calls happening. Trust me, the first time I was debugging the create statement, I was literally pulling my hair that why is the parser being called so many times? Why are so many internal commands being called? Then you keep reading about it and then it makes sense to you that okay, master table, temp master and all of that. So it has taken a lot of effort, but if you think it was worth it, please do comment. Please consider sharing it with your friends or with your social media people. It would really help me a lot. Like, you have no idea how much it would mean to me. It is literally morning. By the time I keep recording, it takes me entire night to record like one video. Just being honest over here and sharing something with you. And if you would like me to be part of your further learning journey, if you would like me to help you with interview prep or with project building, do consider signing up for any one of our courses, LLD, HLD, DSA, HHLD. There's a lot on Educosys. Go check it out. I would love to teach you live or to be part of your learning journey and make it more faster, quicker, because YouTube has its own limitations. I don't know you personally. If you would like that connection with me, please do consider signing up for Educosys. Otherwise, see you next time. See you in the next video. Please do comment and let me know if you found this helpful. Bye.